Which one is it? This one.
So, is this the title you have under the live stream?
Yeah, and this image as well as the thumbnail. I just figured out how to put thumbnails on it.
Okay.
So it's pretty good. So you can make your own thumbnails if you want and send them on to me. Yes, so the title is quite poetic, really. Oh, if Gerd joins, I won't be able to see any problem. What I can do is I'll just a bit of an interlude at the beginning. Rajan, will you be able to see if Gerd joins?
Let me check.
Because then you can tell me and I can let him in. So, Rajan, you still there? Rajan? He's not.
Oh, thank you. Can you hear me now? Yeah,
Yeah.
I was searching for Gerd and it got switched off somehow.
Oh,
I
okay.
pressed
So
the wrong button, maybe.
no problem. But he's not there anyway. I can see that.
Yeah.
Okay.
Yeah, I'm not able to. I think only you can see whether Gerd is coming
Okay.
in.
So you could hear that anyway, though, what I was playing, could you? Bit of a...
Yeah, I could hear you.
Oh, okay, good. So yeah, I can't see anyone when I'm doing this, so I didn't know if you were in or not. So those sounds were from they're like sonified sounds from anomalies from the Earth's geomagnetic field. So yeah, so we see the title Earth's Earthquake Precursors, the distant echoes of the Earth's electromagnetic fields. So a quick bit of project background. The aim of the research is the application of creative machine learning and deep learning solutions to detect anomalous seismic precursors in the Earth's geomagnetic field. So it's mainly dealing with geomagnetic data and earthquake data from the USGS as well, so for earthquake prediction. But other applications could be network intrusion, credit card fraud, cancer research, and financial markets. So the research is funded by European Space Agency, data from SWARM. So this is the SWARM constellation. It was launched in 2013. There's 3 satellites, SWARM A, B, and C. And together they give a 3-dimensional mapping of the Earth's magnetosphere to provide a better understanding of the separation between the core and lithospheric fields. So what I decided to do in terms of anomaly detection was start simply. So the simplest method I could think of and that I could find was the KNN machine learning method. So it's primarily for classification. So if you look on the right here with this diagram, we have like k equals 3. So there's 2 classes of dots here. There's the yellow dots and the purple dots. And so the new or test data is the red dot. So we want to know which class does this dot belong to. And the way we do it is using KNN, and which stands for K, which is the number of nearest neighbors in a sense. NN is nearest neighbors, and K is the number of data points being observed. So if we look at the big circle, K6, there's 4 yellow and 2 purple. So in that case, you look at the Euclidean distance metric between each dot with the red dot, essentially. And then you find the closest one. And then, so then with k equals 3, it's like a majority rules situation. So in this case, with k equals 6, there's 4 yellows, so this becomes a yellow. But if it was k equals 3, then the dot would be purple. So that's the difference. So, but for anomaly detection, we generally only look at one class. And for that, we just use the Euclidean metric. But it is still a type of classification because we're saying whether it's an anomaly or not. Another important aspect of anomaly detection is anomaly location. And to do this, I applied the NumPy all-close function. Right, so the first derivative or application of the all-close function locates point anomalies. So an example of a point anomaly would be a large transaction in a bank account. And the second derivative locates collective anomalies, numerous large transactions in quick succession. So essentially just a collection of point anomalies. So the first sort of version of KNN all-close anomaly detection and location method was called BEAD. And it was only able to detect like the beginning and sort of maybe the end of an anomaly, but not all of the anomaly. So what I did was I also included the inverse of whatever data we're looking at. And this became the second iteration of the algorithm, which was called SEED then. So, and you can see it sort of detects more of the anomaly, like the breadth of the anomaly. So that was an improvement. Here are some examples of SEED detecting faint anomalies and in quite large data sets of like over 1 million data points. Yeah, more successful examples. SEED is capable of detecting weakening and increasing anomalous signals, provided they're above or below the threshold of the main signal. So you see here, it didn't really detect much of this anomaly, really, but only a bit that stuck out below the other signal, or in this case, also below it. So the limitations of the SEED model was that it's not really able to detect reduced intensity anomalies because it's a metric distance thing. It's only really looking at peaks and spikes, either in the positive or negative directions. This benchmarking data is biometric, which is not exactly applicable to swarm data, even though it is electromagnetic in its origin. Yeah, swarm data generally is, we would be looking in the geomagnetic field at spikes in the data for anomaly detection, or more so for earthquake prediction. But depends. If you're looking at total electron count, you might be more, in total electron count, you're only looking at positive spikes, for instance, definitely not negative. But some researchers have found that the geomagnetic field begins to reduce prior to an earthquake in the nighttime phase of the geomagnetic field, because it's tidally locked with the sun. So yeah, there are possible solutions that I was looking at the time, including Fourier transforms, which would apply more to this kind of biometric ECG data, but or you could use LSTM and try and predict, train it on a normal part of the data set, and then try and predict the rest and use the all-close function to find the difference. But that has its own problems. So instead, I'll show you this first before we get on to the solution I chose. This is another benchmarking test using the New York taxi cab data, and this is once again the SEED algorithm, because it's able to detect collective anomalies as well. So this is the demand for taxis from over a year period, from 2014 to 2015. So right at the beginning, it detects an anomaly which corresponds to a lightning storm. Then the next anomaly it picks up is Boston Red Sox versus New York Yankees. Then we also have Red Sox versus Yankees. These are two baseball teams. New York Giants versus Dallas Cowboys. You see the Giants again there. So this suggests that these are important games in the season, and that the New York Yankees, seeing as how these people are all from New York, that the Boston Red Sox are most likely their biggest rivals. And indeed, if we look online, that is true. We would also suggest that the New York Giants that their greatest rival is the Dallas Cowboys. And this is true as well, but it's not necessarily true for the Dallas Cowboys. Their greatest rival is apparently the Redskins, or at least it was back in around this time. So along with this, we have the New York Marathon, which is a big spike. It found that. A couple of other games, and then three more storms, sorry, the North American blizzard as well. And then Christmas and New Year's. So in general, we see that most of the anomalies in New York seem to be based around either sporting events or bad weather. This is going back to the BEAD algorithm again, just attempting to show the different anomalies in the geomagnetic field. These are some of the parameters used and the processing. And this is another version, again, using BEAD. This is SEED, so you can see it's picking up a lot more anomalies, as well as these darker lines, which suggest that this is a collective anomaly here. Right. So matrix profile research. The way of looking at I'll just give a bit of background to what matrix profile is first. So matrix profile is similar to KNN in that it looks at the pairwise Euclidean distance so in this case within the same data set. So you might start with this, and then this black box will move along, shift over 1 point each time, and then take the dot product and put it down here, and then shift over again and take another dot product and put it here. So 0 would obviously be when they're both aligned, and then it will take the smallest value, so that will be 7, 4, and then it can put that into a grid, which becomes ON. So it's quite fast in terms of what it does. Yeah, and they use just in time as well. So Christian was talking about that before. There's a couple of other things to note about it. I guess there's it's very similar to convolutional neural networks in its application using cross correlation. So CNNs could also be used as anomaly detection, and they are quite using different edge detecting kernels. So we might look at that later. You can also see padding method in the CNN method to extend, map, or mirror the data, and therefore eliminate dimensional reduction or cutoff, which is a problem in the matrix profile actually, because as it goes along, these black squares here will never be filled in because of how it works. So if you were to start off the grid and move in and also move off the side, you would eliminate the cutoff. We'll look at that later actually. So yes, this is a comparison between the seed data we saw earlier, anomaly detection, and the matrix discord anomaly detection. And we see that the discord picked up a lot of different anomalies that the seed algorithm didn't. For instance, got Independence Day there, 4th of July, which is an important one. Labor Day, and it got that, but so did seed. So we can see the agreements down here: the marathon, Christmas, New Year's, and the blizzard. There were partial agreements with Independence Day, and yeah, that was here, Independence Day and MLK Day, which is way over there. So partial agreements there, but then there were lots of disagreements, including Climate March, Comic-Con, Thanksgiving, Grand Jury. So all of those, and then. But also we noticed that the Discord didn't pick up on many of the sporting events, such as Raiders versus Jets, or one of the winter storms, which I think was this one. Yeah. So, and it seems to be the reason why is that there's like here and Thanksgiving, it's a limitation of the seed algorithm where it's not able to detect reduced intensity anomalies, but it is much better seemingly at detecting spikes. So the idea would be to combine the two of them to get a better anomaly detector, which is what I attempted to do here. But so I think this is better, but it's not perfect. There's some problem with it that I need to iron out, which hopefully I'll do later. Data visualizing streaming. So these are just other methods of visualizing anomalies. This isn't exactly finished yet, but so this is more data from the swarm satellites. What I need to do is, so obviously you'd be streaming the data in, and there'd be another trace which would highlight where the anomalies are in this data. Could be a useful way of just visualizing the data, really. And another way then is to sonify the data, which is what we were listening to at the beginning of this presentation. So here's the kind of simple enough code to do that using a Python module called Scamp, which interestingly enough also uses matrix profiles, I believe, to generate the sound. somehow. So yeah, so just for a bit of background, the matrix profile was developed by Eamon Keogh. I'm not sure who developed SCAMP. I've forgotten his name, but he has a YouTube channel, I think. So here we go. So this is my own version of matrix profiles, a bit quadratic and constant matrix profiles. So we look at, we can also find limitations with the matrix profile, just as a bit of background. So here we have random data with reduced intensity anomalies at different locations within the data. And we see that matrix profile identifies this as an anomaly, when it isn't actually an anomaly at all. It's basically within the same averages as all the rest of the data. Then if we look at this output, we see that indeed it does. So it only puts one discord in here, which corresponds to this, but misses out these two areas here, which are the reduced intensity anomalies, and doesn't flag them as anomalies at all. But this is still pretty interesting. I mean, you could maybe run the all-close function on this and recover, but it wouldn't get the entire extent of the anomalies, only maybe this spike here and this spike here. But that remains to be seen. So these matrices I was using in a previous presentation, which I'm not sure is online, or maybe it is. No, I don't think it is yet. I would need to edit it. But yeah, I mean, it's technically a part of this, all of these diagrams. I'm sort of using them in a different way. So we go back here. So the idea here is that we have a sequence, and then we take we're moving the sequence over and then summing, which gives these kind of quadratic, how do you say, symmetric sort of results. And then all of the results are also symmetric with each other, in the sense that you have these two values are the same on either side as this one. And when you do this with like any data, random data, for instance, you're going to get this red trace, which is kind of quadratic in its nature, sort of like Gaussian distribution. This graph is, so it's taking the random data in the background and then using that matrix profile, quadratic matrix profile thing I just showed you in the previous slide, and applying the all-close function. So that's the kind of results you get. Not really too useful. Here's even with a larger data set, you can see the quadratic curve even more clearly. Still not useful for anomaly detection or much else. So moving on from that, then you can create a constant matrix profile, which is simply removing the quadratic curve by, like I said earlier, starting on the outside and going all the way out to the far side as well, and then summing all of those as an example. But then that implies that you can just rearrange all of this into this sort of square grid, and it gives you the exact same results. So that's what this piece of code here does, essentially. Yeah, so when this is done, when this is applied, we see that the all-close function goes all the way without any quadratic curve. Oh. Is there anything more to say about that? Not sure. I don't think so. So, right, so then this is more, I think this slide is in the wrong order. If we look at this one, for instance, we have, we're using the constant matrix profile method, which you notice doesn't have any cutoff at the end like the others did. I think you can probably see that most likely in here. See, this is the data, but this data doesn't go all the way to 400. It stops at like 375. So that's the cutoff I mentioned. We can eliminate that cutoff if we go all the way through using this method, which is perhaps useful. And you can also mirror the data like we did with the CNN kernels. Right. So what we're noticing here in the end is using a different, instead of using all close or summing it or anything like that, we can use like an inversion group blending equation, which is simply this, the absolute value of a minus 1 minus a. And this does, create some kind of large gulf between the low intensity anomaly and the second trace. But as pointed out, it kind of, this is on the same level as all the others, so this won't be isolated. So we need to go further. In this example, then, this also includes a rolling blending anomaly detection where we shift the data, let's say 3 indices to the right and 3 to the left, and then apply the same function again. And the idea is that it's meant to create even more shear sides, so that when we run the seed anomaly detector, it without fail detects this and these two sides of the low intensity anomaly, but it also obviously detects a lot of other stuff that we don't want. A way to speed up the matrix profile discords using Python, like C would obviously be faster, but is using Python, and it also helps speed up KNN, which is also very heavy in terms of time complexity, is to use the upper triangular matrix, and this again is the code used for that. So with reduced anomaly detection, then basically once, let me just go back here. So what we do is we once we finish this, we look at the beginning and end of, so there's the start of this anomaly and the end of this anomaly. We can check that using matrix profiles, and then do the same for all the beginnings and ends of all the others. So it kind of moves along through the whole sequence. What the result is this. So you get a peak right where the reduced anomaly is. So it'd be nicer to get it more focused. If we were to run the constant matrix profile again, it would narrow down and get better. You could also use half width at full maximum, but the results are very domain dependent. So that's a problem. So for instance, if we look here, we can see a slightly more complicated example where we have 2 reduced anomalies and then followed by a third. So we see that it finds the first one, but it finds the second one and joins them both together. And then it does go up to get the third one, but not very far. So this could possibly be improved by going backwards as well as forwards, which is interesting because the high intensity anomalies needed the normal data as well as the inverse data, and the low intensity anomalies could probably be improved by bidirectional forwards and backwards, which would obviously is interesting. So you have like 4 directions in the data. So that's kind of the end of the research I've done into matrix profiles as far as I got. Hopefully I'll do more in the future. But for now, I'd like to talk about earthquake preparation zones, specifically the Dobrovolsky radius. So here's some examples of the Dobrovolsky radius that I was able to map in MATLAB. For instance, this is the Turkey-Syria earthquake in 2023, which had a magnitude of 8.7. So you can see that that is the preparation zone for this earthquake. The epicenter was around here somewhere, is very large indeed. So really, this is just an area where the fault lines are cracking and repairing all the time up to the point of the main event. So the sort of the main shock, it was called. And then we have the Aegean Sea earthquake in 2020, or the Greece earthquake, which had a magnitude 7. You can see that the Dobrovolsky radius is much smaller in this case. Once again, preparation zones of Croatia, which is a 6.4 magnitude earthquake, and the Mexican 2017 earthquake. There was 2 earthquakes in 2017 of large scales near Mexico. But a quick literature review on this, or just for other examples really. This one comes from seismo-ionospheric anomalies possibly associated with the 2018 8.2 Fiji earthquake detected with GNSS tech. So that's total electron count. Quoting from this article, which is part of Elsevier, the red circle shows the Dobrovolsky region around the epicenter. So this is Fiji, then this looks a bit small to me, given that it's such a large earthquake. But if we look here, it goes 180 degrees to 150 degrees east, and each degree is like 111 kilometers. So it should be correct. So I'm not entirely sure what's going on there. But if we look at an example of the MATLAB graph that I made versus the Elsevier graph that we just saw from the earlier paper, we see that indeed, according to the equation I use, the radius is much bigger than what we see here, orders of magnitude bigger. So further comparisons from a paper called Gravity Waves as observed from SABRE and a time satellite during large earthquakes. And this is from Hindawi. The interesting one here is the Chia Pass earthquake that I mentioned earlier, which was also happened in Mexico in 2017. And we can see that it's a much larger preparation zone than we might expect. So that was also an 8.2, and it's quite a large preparation zone. So that suggests that the one in the Elsevier is wrong, or there's maybe they use some other method to determine it. And just for comparison again, there's the Puebla earthquake. So they do seem to be, this one's larger because it's 8.2 instead of 7.1. So this is a paper that I helped produce. I didn't do much in terms of the research. That was mostly done by the supervising team and Shane Harrigan. So it's called Sea Martingales and Seed Comparison. And this is for the Greece Aegean Sea earthquake that we spoke of earlier. You can see that they're taking data from around about a year. Yeah, just under a year, I think. And so the event date is here. And then we have 3 months before, 6 months before, and 9 months before. And they've used data from swarm A, B, and C. So they also looked at 3 months afterwards, just to get the aftershocks in terms of anomalies in the geomagnetic field, and foreshocks. And they discovered, I think it was around, I don't know, maybe 15 anomalies at most, something like that. But we can compare that with the seed algorithm, and we see that this is slightly different. So, for instance, the event date is here right at the end, and I looked at 7 months worth of data. So this is just this big block here is the geomagnetic data as it appears after processing. This is how their geomagnetic data appears after processing with Z martingales. It's much more blended, like it's averaged out almost. So this detects a lot more anomalies, and there seems to be a certain spread. This is a very low detection sensitivity. You could really up this and get an awful lot more data, but I just went for the lowest to be sort of the most stringent with the data, because anomalies are meant to be rare and anomalous. And the next thing we can look at is the Rikitake law. Earthquake precursors in Japan, precursor time and detectability. So the Rikitake empirical law is quite important or it turns up a lot in some research to do with earthquake precursors. Essentially, it is the log 10 of the delta of the time, with AB being two sort of randomish coefficients and M being the magnitude of the earthquake. So there's the original paper from 1987, and here's another more recent paper discussing it. So if we look at the Rikitake error ranges, we see that A and B, the coefficients for the worldwide geomagnetic field for an earthquake of magnitude 6 have the error ranges like so. So this would be plus or minus 0.78, plus or minus 2.08 times 6. And what I found from just doing that out was that the range with those error bars seems to be anything from 0.6 of a day, whatever that is, a bit over half a day, maybe 13 hours, 14 hours, up to 398 days in the mid-range, and what works out to be about 703 years, which seems a bit surprising and makes me wonder if the calculations aren't a bit off. But even if they weren't, I mean, even with like a vague, a midpoint of 398 days, it's quite, I think this is the value that they use. So this is meant to be the main geomagnetic anomaly for shock event that's associated with the main shock. But yeah, well, we might see some examples later on. So, well, just to go back here. So, yeah, so it basically with the data, it doesn't. Maybe we could go back and see. That would be, I don't know. So let's say this was like, well, we don't have 384 days there, so it's not really that useful. But you can see that there's a lot of anomalies, even in this stretch of 7 months from the seismic event. So why doesn't, if it's covering 0.6 days to 398 days, then there's an awful lot of geomagnetic anomalies that could factor in there. So it doesn't seem that useful, really, for my research. Maybe there's a different way to apply it that I'm not understanding. But so my idea was to use a logarithmic spiral instead. So if we imagine that the spiral terminates here on the 0 axis at the very center of the graph, then we could place the earthquake there, and this is going backwards in time towards the 180 degree point. So if this is the timeline as it's moving towards the earthquake, we'll see an electromagnetic anomaly here, one here, here, here. This could be like a month before, and then loads just before the event. So it gets increased. And then afterwards, it would fan out again in the opposite direction. So it's kind of like a time spiral, almost like a complex wave moving through time, as if the event, because like earthquakes are such big events, and yet they have this effect on the very small, like the quantum scale, and we know that the quantum scale is sort of time independent in a sense. There's no causation there. It can go forwards or backwards. Be interesting if earthquakes were able to send precursors back through time, like echoing through time. Sorry, I skipped ahead there. Obviously, I mean, that's kind of a left of field theory, but it's, you know, it's just, I guess that's a different way of saying, instead of saying you're predicting earthquakes, you're kind of detecting the temporal anomalies of the seismic event, in a sense, or the temporal detection of an anomalous seismic event, which is useful in terms of the topic. But not really, because we're perfectly able to predict anomalies for earthquake prediction. There's nothing wrong with that. So this is using the logarithmic spiral. There's the equation for that, where this is the natural logarithm, two coefficients, and theta. And then but other options could include the Archimedean spiral and the hyperbolic spiral. If you look at the Archimedean spiral, we see A plus B times theta, which is very similar to the Ricci-Take law anyways. So I wonder if he was not inspired by this same idea, tried to apply it. If we go back, then we might be able to see, yeah, because you can see there seems to be some regularity in the spacing. So if you had here and here and here as well, so if you had a kind of an Archimedean spiral, you could imagine that it would join up with the events quite well in places. I mean, that's one of the things about empirical laws. They're observed laws. That doesn't mean that there aren't many more laws that could explain the same thing or better, or in combination that they could explain them better. So maybe if we combined all of these together, we might have a better match. So that's what I tried to do. Well, so far I've only successfully managed to do the first one, the logarithmic spiral, because I only thought of doing the logarithmic spiral to begin with because, of course, earthquakes are measured in log 10, and there's other factors. Well, for instance, the log of the time delta that Ricci-Take used. So I figured this red line up here, I chose these coefficients A and B so that the red line here would exactly coincide with the 398 days of the Ricci-Take, or I think it's 389 is the sort of optimum date that they choose. As we can see, there is no anomaly here, but there are anomalies nearby. I would say that the bigger one is here. If it had joined up with this, I'd be more impressed, maybe. But I suppose it's just down to personal opinion. So if the spiral, the outer arm of the spiral terminates here at the sort of optimum point of the Ricci-Take law, then we see that there's at least two times that it crosses close to the event. This is the event itself, crosses here, crosses the timeline again here, which is close-ish to these, but so there's obviously, this is a failure, I would say. So so I did two more examples, and these are kind of the time quake idea I was talking about. But in the top figure, we have logarithmic coefficients of A 0.78 and B 0.08. And the bottom figure, we have the coefficients. Once again, A is 7.8 and B is 0.078. So the top one, it's pretty similar. It picks up the earthquake. Then there's one event there. And then right in the middle of this big mass of events that we thought was interesting before, that's where we get the next one. So I think that's quite good. This one also works well because there's generally thought to be anomalies like a month prior to the event, you know, as well as earlier with 6 or 7 months prior. So this one is also bang in the middle, so it's quite good. But really, yeah, like I say, so you can see the sort of regular spacing here again, which the Archimedean spiral, I think, would probably pick up on. Maybe another Archimedean spiral of a different intensity, I guess. Different coefficients might work. So next I want to just look at deep learning applications. Can we predict earthquakes with any of these methods? And to begin with, I tried to train an artificial neural network on the seed algorithm data, the anomaly detection from the seed algorithm. So this is really just a classification tool. Can it scan data, any data really, but let's say swarm data, and correctly specify whether something is an anomaly or not? Yeah, so this is on a data set of around 50,000 observations. It should have slightly more epochs, as someone pointed out recently, but the accuracy is quite good. It's 93%. There are other methods you could use, precision recall, F1, and a different kind of accuracy based on false negatives and false positives, true negatives and true positives. And those also give quite high results. But in a sense, yeah, I mean, in a sense, there's not much point in doing this, because if you're already detecting the anomalies, why develop an artificial neural network to do it? But I mean, there could be reasons in terms of generality and stuff, but it is what it is. So, but we can, you know, train the data on information from swarms, such as the longitude and latitude of the satellite, the F field. This is the residuals of the F field to do with the magnetic core. And then we have the radius, which is how high the satellite is, the anomaly score from the KNN anomaly detection, Boolean, whether it is an anomaly or not, and the anomaly truth, which is simply the Boolean times the anomaly score. So then we can take data from the USGS this time. This is the latitude and longitude of the epicenter, sort of with the depth, and that would be the hypocenter. We have horizontal error, depth error, and finally magnitude. And when we train an artificial neural network linear regressor on this, we train it on each one consecutively, and we wind up with quite a high result as well, even with quite low epochs. So yeah, so the end result is something a bit like this, but oh well, actually for this, yeah, we get quite a high result on each of these, but where it falls down actually is with latitude and longitude. We get very bad accuracy on these 2 points. So in order to achieve better accuracy with them, we need a different approach. And so the approach that we use is the earthquake catalog. So just get out of this for a second and show you some of the actual code used. So here we're downloading the magnetic data, and then that's the data frame there. Then we download and process the we see the earthquake data. Yeah. So there's the latitude and longitude that we're interested in. Depth is also important, but it's not included in this study, I don't think. Magnitude and some of these other important factors. Then we run the anomaly detector on it, graph it. That's sort of the pipeline used. This isn't showing any yet, but here's the catalog that I was talking about. So first we just have we're looking at geo coordinates that are 10, you know, it's in a step range of 10 on both the latitudes and the longitudes. There's a time series there. So we start off with a matrix of all zeros, and then we start inputting. You know, let's say there was an earthquake happened on the 1st of or 6th of January 2014 at this time, then we would put, and in this location, then we would put a 1 here, and then it would continue forever because that earthquake is counted then. Same with over here, there's more earthquakes counted. And oh, I don't have a tail output for that. Should be useful. But essentially, at the tail of this, oh, that is the tail. So, excuse me. So there aren't many earthquakes here, obviously. But you know, we'd expect to have like 4s and 5s and 3s and stuff like that. So there not a huge amount of earthquakes occurred during this period of time, and this is worldwide data, obviously, because of all of this. So I'd need to get a better data set in order to get more anomalies. There is another data set that I used, though, which was from 2016, which we'll look at, and that was also global. Here is our regressor, and you can see that each one is trained with varying accuracies. It goes on and on like that. And it's trained on quite low epochs because there's so much to train. So that's the reason for that. Is there anything else? Okay, so we'll move on to the earthquake visualization copy. Now, I have a funny feeling that I have to run this from the start. So we'll do that. So yeah, so here's once again our earthquake catalog. 2 earthquakes here, 1 here. You don't see any jumps. There's the length. This is the number of features, 13, because that was how many coordinate points in the entire world actually had earthquakes, and that's the number of observations in total. So close to 140,000. So let's just keep running these. It's the head. See what happens. Now, yeah, so now we get into the visualization process, because we're going to attempt to make an animation of all the earthquakes and an animation of the predictions. So that's what these are. It's going to generate a heat map, I think. Oh, it already did. Okay, so wondering actually if I were to put in render equal browser, then view on this. Oh yeah, okay, that doesn't work because it doesn't pick up the map in the background, so we'll leave that. And I'll just rerun it like that. So it's nice to have the map to kind of give it the idea of the globe. I'll just go check on the stream. Oh, okay, we're still live. Just checking. Okay, so I'm gonna play that. I assume it's already playing. Now, according to my records, this, you know, checking against the ground truth anomalies, or not anomalies, I mean earthquakes. This method detects the correct location and timing of an earthquake in this region, which is, I guess, latitude 34, longitude 11, somewhere in that bracket between 34, 35, and 11 and 12. It happens kind of late into the actual, how do you say, animation. So while we're looking at this, I mean, we can see that all of the earthquakes happen in this location in sort of Southeast Asia, north to Pacific. So the Pacific Ring of Fire, a couple down here in Southern Australia. So I think there may have been a flash there where it goes up and then goes up one and then down one. It's 9 there, 4, oh, wait a second. Yeah, 9, and that one changed from 4 to 3. So obviously that's not right, because it's supposed to count up, but and it's changed back to 4. So we can see that it fluctuates. This one's gone up to 2. So at the point that that one went up to 2, that was when the earthquake happened, roughly. We're pretty spot on, actually, and in the right location. But we can see that it's making errors everywhere else. So I think this one's changed as well. There was no earthquake there, and so on and so forth. Just pause that maybe. I don't know if that works. Not sure if this is going to be much use, but we can go and look at it anyway. This is just an example. You might use something like this to check against the ground truth, but I don't actually have a ground truth available in this particular instance, so it doesn't really matter. But basically, when I increase the date time here, it's just going forwards another 10 seconds in time. So we can do that here. We've gone forward this number of seconds. Oh, hang on, I'll just make sure it is in actually 10 seconds. I have to look here. Mm-hmm. Oh no, sorry, it's every 1 second. Excuse me. Not entirely sure. I don't. It's been a while since I looked at this. Okay, so yeah, so you can run this, and then we can. This might be very useful if we don't have that. Yeah, like I said, I haven't looked at this in a while, so this might be a bit. Might not be very useful. I don't know why I have ground truth here when it's not going to show up. Yeah, basically, there is a way to display this where you see that the change happened at the right time, but I'm fairly sure you trust me on that. So yeah, okay, so let's go back to the presentation. I think we're nearly at an end, nearly at the last couple of slides here. So, well, that isn't that successful, really. We did pick up one, but I've done subsequent tests with the data from 2014, obviously, which didn't have too many earthquakes in it to begin with, so it's actually probably not very useful, but might be more useful to use an LSTM anyway. That would probably remove the fact, the way the numbers aren't counting up all the time, they go down and up. That's not good. So an LSTM might be able to correct that. I still haven't implemented that yet. But another method that might be very useful could be Q-learning, and another method called deep Q networks. So the Q-learning table is on this side. It's kind of hoping to show Gerd this because it seems to be a bit related to his Q factor in a way, but only this is not really frequencies. It's more, yeah. So this is reinforcement learning. So we have the states on this side and the actions here. So we'd have our agent who needs to take an action within the environment. And the way it chooses to do that is using this thing called the Q table, which is the state and the action that so given the state, like given the location of it on the board, for example, if it's a chessboard, and then the action is which direction it can move, which would be a series of action based on the pieces, I guess. And then it basically tries out every single action possible and gets the reward or the penalty based on that action, and then fills in the Q table with the value. So if there's a 1 here, let's say, and a -1 here, and it starts here, then the tables of the Q value are going to go down as it approaches -1 and up as it approaches 1, and it'll level out here as well and along this line. So it will greedily choose the best route. So it would go like across here to -1. I'm just using that instructively. That's not how the table would necessarily look. With the deep Q networks, we are kind of replacing the Q table with a neural network, and the Q factor, or not the Q factor, sorry, the Q learning value, the rewards and the actions. So the states go in here in the input, and then the hidden layer is the weights are the actions and the rewards. And then the output in this case is binary, which is good because it would just be that's an anomaly, that isn't an anomaly. If we were, if we were to use Q learning in an anomaly detection sense, which is what I'm suggesting to do here to begin with. One question we could ask is, Q learning is often called reinforcement learning, and a kind of, hang on, I'll take a drink of water. Unsupervised, which means that it doesn't need labeled data. You just kind of, so I suppose, I mean, does it or doesn't it need labeled data is the question. So if we look at this taxi, this is our agent, and this car park is the environment. And the possible actions it can take are up, right, back, and it can't go left because of this wall here is blocking it. I initially thought that this was a penalty of some description. Maybe this would be, because this is a man holding a briefcase with a purple circle around him. So if you were to drive your car around here and run him over, you would get, oh, sorry, that would happen. No, you get minus points. And if you were to drive up here to your destination, obviously, you will get full points. So the agent wants to maximize its reward function. It will drive around everywhere and crash into the sky and then learn not to do that in future. And then, so this would be a terrible, terrible thing to have in reality. But for a computer game, it's fantastic. And then finally, it will learn the right thing and will always drive right to its destination each time to get maximum rewards. But we have to understand that from the computer's point of view, driving into the person holding the briefcase or a car or another car or a tree is perfectly fine. The computer has no problem doing that. It doesn't mean anything to the computer. However, once we so that it's arbitrary from the computer's point of view where it goes. It doesn't matter. But we as humans, we want a certain outcome, so we set what we think should be the rewards. In this case, this location just happens to be this location. And what are the penalties, which is, preserving human life, which is obviously, and, you're not causing havoc with trees and such. So, yeah, so the rewards and penalties are set by the user and or programmer, depending on the system we're using. With deep Q networks, there are, so basically what I'm saying there is, it's unsupervised, but sort of supervised as well, because this information needs to be labeled in order for the thing to work. So we need to label our data as well. So how do we go about labeling data, which is, as we've seen previously, with 140,000 or 1.5 million data points from the seed geomagnetic anomaly or geomagnetic data, how do we go in and label all the anomalies by hand? It would be very difficult, take a lot of time, and you'd also need sort of an expert understanding of the data, which not everyone will have, maybe nobody. So the previous use of the deep Q networks for anomaly detection have used active learning, which is basically human feedback. So they are labeling the data, and then the deep Q networks go off and try and predict based on their supervised data, and then they come back and get more of a help from the people. We just can't do that. It's too time consuming and resource consuming. So my suggestion would be to combine the seed and the Creus. The Creus was the, we sort of skipped over that a bit, but it was the combined reduced intensity anomaly solution, essentially the matrix and constant profile. Or we could use matrix profile, although we have seen that has some problems. So I might use Creus instead once I get it up and running, and combine that with Q learning so essentially that's how we will set the the anomalies. So we want it to detect an anomaly, so it gets 1 point for detecting an anomaly, and maybe 0 or -1 for detecting a non-anomaly, and then gradually it should learn just to detect the anomalies. So we want, in order for it to know which ones have what the value is for each data point, we need to tell it that, which means that we need to detect them in the first place. Now, that's again, like, why go through all this trouble if we've already found the anomalies? Well, in this instance, we could get an even better detector, and you could train it on like new data, and then it would be more efficient, because KNN is, well, actually Q-learning is pretty under efficient in this sense, but it has certain benefits from the point of view of generalization as well. So yeah, so we'll move on. So the concept I had was to use, well, initially I thought of using sort of a Mexican hat topology. So this is like the start, and then it goes out in 3 rings. So you would have the reduced intensity anomalies around the inner circle here. You could either have the high intensity positive anomalies or negative anomalies here, and same on this one here. So the anomalies would be essentially sorted. Either they would be sorted using the Boolean and anomaly score to go either here or here or there, and any data points that are just in the middle that have like a kind of a low anomaly score, except for the reduced intensity anomalies, which we are interested in, will be in the trough of the sine wave, essentially. So they will not be detected. And the reason why they won't be detected is if we look at the z-axis here, and imagine that this is 1, this is 0, and this is -1, then as it goes down, as the Q-learning algorithm agent goes down into the trough, it goes into the minus. It doesn't want to be there, so it goes back up here, and then any data point that happens to be sitting here that it encounters, it will give, it will output that as a correct anomaly, whereas it won't for any of these. Oh, well, it will for each of the peaks of the data sets. So that's the concept, and then obviously this could be, how to say, ported out to the DQN, to make it more, I guess, just to make it more efficient. Essentially, that's what it does, and it was also be very useful from the point of view of earthquake prediction as well. So, in that sense, I'm thinking of calling it the deep quake network, which I think has quite a good ring to it. But in any case, yeah. Oh, yeah. Well, another point here to make is that this kind of circular structure for the graph is probably not. It's a little bit complicated, so it'd be better to just use a planar wave and have the anomalies on the peaks and the normal data kind of closer to the middle. So, so that's it. So thanks very much for your attention, and I'll stop sharing my screen.
Yeah, great presentation. Thank you.
Oh, great. Thank you.
Yeah, it was
very quiet during that presentation, Rajan. I got about 3/4 of the way through, and then I was like, am I doing this by myself?
yeah. No, I didn't want to interrupt your presentation, but I thought.
Oh no, you're dead right. Yeah, it's good. Yeah. Just I wasn't sure because you can't see anyone, so it's hard to know.
Yeah.
And then I was like, I'm not even broadcasting.
Yeah, it can happen like that. It's kind of monotonous, but sometimes, because if you interrupt, I think your flow could be affected. So I thought that maybe better.
Oh yeah. That's kind of. So yeah, well, yeah, it was tricky enough presentation to do because there's a lot of work. There's a lot of work in that.
Yeah, a lot of different.
Yeah. And so I kind of, some of it's going way back, and I was like, oh yeah.
Yeah.
Like I would deliver those presentations as I kind of did them separately, and I really knew like exactly what I'd done. But then this time around, I was sort of I had to sort of work it back. I had to work backwards to what I'd done, especially for the combined reduced intensity anomaly solution. Like, I mean, technically, I could look that information up now. Am I stop? Am I share? Oh no, I'm not sharing. Let me see if that can be done. Share screen. Entire screen. Yeah, share that. So, no, still on the wrong one. All right, so I think we can go. Oh yeah, or else, well, I probably shouldn't share because it could be copyrighted. Reuse slides. Reuse slides. I think it's. There's that presentation I did recently. I think it is in this one. And then, yeah. Right, combined reduced intensity anomaly solution. If you just look at that, it's reduced intensity anomalies, which I think is in here. Reduced. I don't see it actually. Oh yeah. Reduced intensities. All right, so this is just random data, and then we probably have to run all of this. Might as well back out of this. Close that. Yeah, so there's the data, the kind of random data. So you see we're using this equation here, which is a sort of a difference equation. And then there's many applications of that.
Is it connected with the Euclidean thing you showed, square root of p square minus q square or something like that? Is it?
No,
is it
not exactly. It's more of you know, when you're using Photoshop and you use the different, what are they called? The different blending techniques. So you can use darken, lighten, or any of those. And this one is essentially it's like an inversion. It is part of the inversion group. But I mean, I think you can think about it in some way mathematically. Where's the equation going? Oh yeah, so like, I think the idea is you're applying one trace. So you have a so one is just all ones, and then the reference minus your data gives you y.
Is that differential? DF is a differential?
No, DF is a data frame.
Data frame.
So it is, actually, where is the data frame? Oh, it's coming in here, you see?
Okay.
Data frame. So it's this list of random numbers is X random list 1. And then we call it DFX. That is this data. So we have to normalize it first in order for this to work, I believe. And then we create another list with just ones in it. And then we minus this from our reference from 1. So all of them from 1. And then we take our original data again and minus what we got from this, and then take the absolute value of that. So that results in something that looks like this.
Does it use like a fixed point thing? Is it like a Is there any fixed point?
You know,
Because
there's a way to look at it. You're essentially. I'd have to look it up again, but I think you can look at it in a way that if this was 1, if dfx is 1, then this is 0, which means that when we have a 1, we get 1 times 0, so 1 is 1. But if this was -1, this would be 2, so then this would become -1, I think. Is that right?
oh, did you fix something and then find out from that point of view is plus or minus, or
Oh,
do
no,
you
well, yeah, I
consider
mean, yeah, if this is -1, then this is going to be plus. So that would have to be 2.
the reference?
So
So the
then we
reference
have,
keep changing. Does the reference keep moving,
oh, then we
or
have -1, -2. Wait a second. Is that right? Yeah, -1, -2. So then that would be, I'm not sure about that, actually. That seems a bit, I think I'm getting muddled up. Sorry there. You see, you can't go below 0. That's for sure. Also can't go above 1. So anyway, I'm making some dumb mistake there. Not in a very good, clear headspace, obviously. So, yeah. So eventually, it's something like that. Like if this was, let's say, if this was 0.5, 1 minus 0.5 is 0.5, and then 0.5 minus 0.5 is 0. So if the two things are the same, or like just in the middle, they will go to 0. But if they're different, they will go up. Yeah, does that make sense?
yeah. So
Kind of
let me try to understand slightly different way. You can correct me if I'm wrong.
Okay.
So you are looking at group of data, right, at any point, and
Yes.
so you are actually
This
you are actually constricting to certain amount of data. Let's say 100, 150, or in that index, or
It's
like
about
a 50 to
500.
100 index, right? Yeah, you're looking at that data and then find a reference point somewhere, and then you find out the difference. Is that one way you are doing it? A
I
group
think.
of data, and you are analyzing, you are focusing on that group of data and seeing whether there is an anomaly in that region. Is that right? And then you keep moving it.
Oh well, no, that is the matrix profile method, like
Oh, okay.
similar to that, or the actual matrix profile method is this. But no,
Yeah.
we're not doing that. We're in this instance, we're taking the whole block of data and just like what's a good way to describe it? It's like if you had. I'm usually good at describing this, or in my head, I can think of examples, but it's like if you had if you had a matrix full of ones, and then you have a matrix full of -1s, and you just add the two matrices together, you're going to get the matrices with zeros. So it's essentially like that, except you're just adding this list. You're minusing this list, which is between 1 and 0, from a list of all ones. So it's just straight line across the top. And then maybe the equation that's a bit more helpful to understand is
so essentially like canceling the base, like you are canceling the main thing, so you can magnify or the small signal. So you are essentially canceling out the big signals, background signals, right? All the other things are background. You are essentially canceling, and then you are just getting the small signal. So then, because you are canceling out the other ones, the small signals get amplified. You can see an amplified picture of that. Is that right?
yeah, I'll just go back. Sorry, yeah. So I think what's happening is it's something to do with yeah. So if you have, it's basically like an inversion. You're inverting everything, but nothing can go below 0, as far as I can tell. Where? So for instance, because it's an absolute value. So if it was -1, then that would be that's 0.
You are shifting the base up in a way, the positive direction.
Yeah. So yeah. So like we said, and then the final one. So if the value is 1, it comes out as 1. If the value is -1, it also comes out as 1. But if it's like 0.5, as pointed out, it will be, I think we said, 0.5. It'll be 0. Yeah. So it's only looking at the large and the small scales. It's a kind of idea that we're doing. So in any case, it has the effect of bumping up anything that's small to the high, and anything that's high goes to low. But anything in the middle just sort of.
It's very similar to small signal amplification.
Yeah, maybe. Yeah, so maybe actually it's anything that's low gets bumped up to high, anything that's high stays high, and anything that's in the mid range goes to 0. Yeah.
So
it's kind of like it's a bit like applying a logic gate to all of the pixels in an image, if you will.
It kind of reminds me. I was doing the masters, especially my masters thesis on looking at pitting corrosion. It's like corrosion, what happens in a pitting corrosion, things like that, of steels, of iron. So what happens is very similar. You get a lot of noisy data. I use something called profilometer. My professor is physics from Harvard. He's an old one. I mean, he was the emeritus professor who was also my advisor. There was another professor who was the real advisor. So they had two.
Pickering.
And I worked with in profilometer, which is used in a lot of this geomagnetic, the earth, the geo signals, where you get the geo signals that continuously monitor, right? The geo signals. So the profilometer is used.
It's a bit like a Langmuir probe or something.
Yeah, it's called a profilometer. So essentially the same equipment we used to find the, he said we can apply the same equipment to find the pitting corrosion. So what happens is it has a probe there. I mean, later on scanning. So it goes there and then, it gets the data. If there is a dip somewhere, it will show up. Then, so it will get you get a data like that. So whenever there is a dip like this one, like a dip, so it will show up. So essentially, it's like a noise. So right now, I'm looking back at it from the physics. I have published that absolute genesis, where you essentially have a noise that is actually totally swamping everywhere. So you cannot see where the signals are, right? Because the signal to noise ratio is reduced. If the noise is very high, the signal to noise ratio comes down. So you have some way of increasing that, how do you increase the signal to noise ratio? That was the thing. So I found I didn't use at that time. I had not used computers or anything, but I used a very simple technique, and it seemed to work. It's a very simple algebraic thing, much more simpler than this. But the idea I was thinking, and I'm going to show you similar thing for superluminous thing. I found, I'll show you after we finish this. Because it's very similar to what you are showing. Maybe we can apply what you have done to that to figure out. It's very similar to find that. It's like an anomaly. What we are saying, a distortion. Like we discussed last time, the distortion within the superluminous is what's creating the particle in a gist. Yeah. So the distortion is like an anomaly in the superluminous thing. So like anomaly detection, like this one, we can find out some way. Then we can figure out how, kind of verify whether our theory is correct in some ways. Like we are pointing out some kind of like Christine was pointing out, there could be an experimental way we can figure out. This may be one way you can figure out. But the anomaly, you had different techniques. You started with retiflac and then D, whatever you call it, D thing, which showed the red lines. And then
well,
what is it?
the red lines was the spiral, the logarithmic spiral. That was for Rikitake. I think there was the first one was seed. Was it the KNN?
No, there was another one, D something, D stuff.
Oh, the first one was called bead, and then that was replaced by
yeah, but D something.
Difference in the equation.
Before that, you show the earlier ones.
Oh.
The earlier graph, you show the comparisons where one of them picks up the things, anomalies, the other the taxi cab and things like that, where one of them picks up
Discord.
Discord score. Discord score. So the Discord score, you said that it picks up some things, but the other ones, it doesn't pick up. And then you use the other technique. What is the other technique? The matrix profile?
Well, no, this is actually, sorry, this is matrix profile.
Okay. So one is a Discord. What is the other technique which is picking up the
No, actually, that's the confusing thing. A Discord is part of the matrix profile. I think I've got the name wrong there. I'm saying matrix protocol as if it's some sort of spy novel. It's matrix profile.
Yeah, I use a protocol quite a lot. Yeah, the word I use, protocol, quite a lot.
It's a good word. It really is. So actually, what I'm Discord is something like, it's basically an anomaly. There's two things in matrix profiles. There's discords, and then there's things called motifs. So motifs are repeat patterns. We can see them all over the place in this. It's quite repetitive. But so a discord is where the repeat pattern is off. Because if you've taken a window size of these, let's say 8 lines, and you move them across, it's going to find a lot of concordances with all of these things. But then if it comes to like here, it's going to find a definite discord, and then so that's why this is quadratic as well. It's kind of going up and then back down. It's because it's a sliding window moving across. Which was partly my thinking anyway when I made when I was looking to create these other reduced.
Which one is picking the green ones? What is the green ones? The green ones in the earlier. Yeah. What is picking up that?
Yeah, this is the KNN seed algorithm with the all close function.
Seed. Seed. SEAD, right?
Yeah, so it's finding all of the anomalies within the difference blending method.
Is it using absolute value? The seed uses the absolute value. What is the equation that it uses for seed?
Yeah, that is the metrics, the Euclidean.
The Euclidean thing. Oh, that one. Yeah, that's what I thought. Okay. So that's a difference. It's like a variance type of thing. Very similar to variance.
Really?
I'm not kind of like variance. See, so that's one question I had. So essentially, it is like finding outliers, right, in a statistical data. So anomaly is like an outlier, but in this case, it's an inlier.
Yeah, of course. Sorry. Yeah.
So it's like an inlier instead of outlier. It's like an inlier because it's kind of embedded within the thing. So it's very hard to figure out. And that's the problem. So you have to pull out that from what is inside, outside. That's essentially you're doing with this technique, probably, right? Trying to pull out.
Correct.
What is hidden inside? What is hidden inside?
We can apply the anomaly to the thing, and it's supposed to pick up like an anomaly just before the rise and just after. So it kind of does it there. Really good. And then if we look at the code, I have to go back in time to see what I did. So I've created a new data frame with the Boolean and the anomaly score. This is our difference value. This is our original data, our reference, and then the resulting Y data.
Is it a combined thing? It's a combined thing of the
Wait a second, I can just go up here and copy this down. And
the Euclidean and this thing.
is it the, yeah, no,
Oh,
actually, this is the reduced intensity anomaly solution. So the actual combined reduced intensity anomaly solution is something else, which isn't, maybe, I think it's something else. So reference is just one. It's just a column full of ones. X was our original data, so we minus X from the ones to get this, to get the Y, and then the difference is the absolute value of X minus Y. And then the anomaly score is, as we've looked at, the anomaly scores.
so essentially, it's like digitizing the data. You are digitizing it.
Right, yeah, in a sense. And then the Boolean is whether that is an anomaly or not, which means it gets a green point or series of points. So
Yeah.
and then we can keep
So,
going.
see, it's a very similar thing. Like you had something called expectation value and extreme value statistics, right? I am thinking about that now. So one of them is that one of them uses average values, the expectation value in general, and the extreme value statistic use variance. But now, if we combine the two together, right, in some way, almost like a Bayesian analysis. So you combine the two, you can actually pull out. It's like inside like a black box, like a Schrodinger cat, right? You don't know what's happening inside, like black box. So you are trying to pull out the information from inside using the many different techniques like this.
Yeah.
So essentially, your hidden data you are trying to resolve. First, you have to. So what I found in that one is in its spectroscopy, there are two important variables. One of them is called resolution. The other one is magnification, or or amplification. So resolution is you have to resolve. So where it's occurring, like in spectroscopy, where exactly it's occurring. And once you do that, you have a very low signal. It is hidden inside a high level noise. Then you have to amplify it once you resolve it. Because if you just amplify with resolving, everything get even the noise, everything. So you cannot detect it. So first you have to resolve it, like in like sodium vapor lamps, for example. How do they find two split lines, right? They occur together, but they resolve it at that level, 0.0 some levels. And once they resolve it, they actually amplify it to figure out there are two split lines there. That's how they find the quantum nature of the thing. So it's kind of very similar, but you are doing more in the computer, more in a general computer simulation or algorithm.
So is that they amplify, and this is a spectroscopy. Darn it.
Technique,
Huh?
spectroscopy technique. Yeah,
Right.
spectroscopy. You have this right all the time. You have like you are analyzing say chemical data. So you have like in a big compound or in a mud, for example. If you find trying to find spectroscopy of a mud, right? You have all the different things inside there. So how do you resolve what is in there? Like if there's a magnesium or iron or something like that, right?
Yeah. Yeah.
So you have to resolve it first, and they occur at specific lambda wavelengths, right? So at what level each one is occurring. So you resolve according to that. Once you resolve, you get a very small amount of signal there. You amplify it and see what percentage you have. And then of course your error limit. If it is within the error limit, then you cannot be sure. So you do some other things, but you can figure out from the spectroscopy, you can figure out what elements are there, and then you have some questions. Some of them are within the error limit, so you cannot be sure. So then you do more sample collection and sampling and things like that. You can do So
Mm.
so very similar. But in the case of your data, you don't have that facility because things are happening in a continuous way. So you have to find a continuous way of monitoring, and it's a slightly different technique. We don't have the luxury of collecting samples, things like that, right?
Yeah,
So you have to. So
in a
that's what is limiting. That's why where your prediction is very difficult because there
mm.
is nothing to sample. You are really real time monitoring. You get data.
Like I mean, they do have like so for instance, with the swarm satellites, there were three
Uh-huh.
of them, and I think the mission began in 2013. But as far as I know, they're like out of commission now. They're still up there, I think, but they're not necessarily collecting data. I don't know if that's the case. Then they must have stopped collecting data quite recently. But I don't know. Maybe not though. So it seems like that we are dealing with a kind of historical and well, just recently
Mm,
historical record. So there's a lot of data. It's 10 years worth of data. But there's also a lot of gaps in that data as well. Whereas and of course we have to introduce gaps as well. For instance, when we are looking at attempting to predict earthquakes like this, you can't include data from the poles because it's way too strong. And there's all sorts of processing that needs to be done. So so this part here, what I was trying to say was, let's say we have the anomalies detected within our reduced um, intensity anomalies within the inversion group difference thing that we're discussing, and then basically it will, because it knows the start and the ends of all of these collective anomalies, and it's in a list. It just goes through and takes the start of this one, the end of this one, the start of that one, the end of this one, and it just goes through all of them, like backwards and forwards, and takes the average of all of the data points from the actual data.
mm,
And then because the average here will be between this and this will be so much
mm,
lower than say this and this, it's it will raise this as an interesting area, and it will keep raising it over and over again as it scans through. And because we know that there will definitely be an endpoint here and definitely be an endpoint here, it is going to just take this anomaly, and it's going to, it might take this from here as well. So that's why we get that's why it winds up looking like a quadratic thing. But the trouble with
yeah.
that is if there's two reduced anomalies next to each other, it's going to
Mm,
just sort of, it's not going to go up and then
yeah,
down.
it gets swamped up. Yeah.
Yeah, it'll just join them together. So because this isn't,
It doesn't have resolution. It cannot resolve that particular thing.
yes, exactly. So I mean, obviously, I can run this in a different way where this will just be a block of ones, I think. So in that sense, I could just take the, I've forgotten how to do that, but it is possible. I think it might be running that or something. Well, it might not be this. And I just run it again. Could go totally haywire. Yeah, it did. Average val does not exist. Oh, what is that? Oh, sorry. Maybe. Will this be a bunch of ones? Okay, it didn't. Let's just graph it and see. Oh, it's completely different.
Oh yeah. Now
That's not
it
very
kind of,
useful.
yeah.
It's upside down, is it? No, I don't know.
Yeah. So
Maybe
the
it's this.
inversion, high intensity makes it low intensity. Low intensity makes high intensity. Is that right? The inversion process in a way.
No, low intense. Oh,
Oh, it keeps the high intensity. Only the low
and
intensity it flips, huh? Something like that.
um, no. If you have like, so we flip everything because we take the absolute value anyway. So if you have something that's very low intensity, it becomes high intensity. If it's
Yeah.
high intensity, it just remains high. And if
Reminds.
it's if it's mid and like middling, it goes low. So it's like an edge detector in a sense. It's going to pick out the differences between. Oh well, no, that's especially true when we do the rolling thing. So I mean, if we had I don't know, if we had like if you just look up like if you take an image, yeah, and then take a second image and just use the difference blending tool in Photoshop and see what happens to it. And sort of play around with it. It's quite interesting.
It's like parity type of thing.
Yeah, I think so. Very much so. Oh, look, there we go. It worked. So you see, you've got this big square. So we could like, instead of doing it with all the data like I just did before, we could just do it in this square. And I think
so it's 0 1 0 1 like binary.
Yeah, because this is all ones up here. So if we just did it in this square,
digital output, like a digital.
Right. But there's still problems with this method because, well, obviously it didn't pick up this one here. So
you have to reduce the width of the square wave somehow. So then
Well, you just take the values of the list from in here and then repeat this.
So reduce the interval. Can you reduce the interval? The index can reduce the interval of the index.
Yeah, exactly. Yeah. You can. So what I would suggest doing then, but you see, you have to know, like, if this is an automatic algorithm, how does it know that it's important to apply the reduced interval here? Because it's not going to know that there's this spike in the middle of the data. So
now once you know it, then you concentrate on that region and reduce the interval in that region. Can you do that?
Well, yeah, you can once you know it, but the question is how to make it automatic in that sense.
So machine learning, you have to do like a machine learning type of thing.
Or there will be some method to figure it out for sure. Like for instance, it's perfectly fine here. Like if we were to take that digital signal that I just showed you here, then we could like narrow this a lot more. I'm not sure what would happen if we did it here, though. I still think that this would just be a big.
No, it shows a little bit step there.
There is a bit of a step. Yeah.
In this one, it shows a step, a little bit of a step.
And also, this for some reason. Oh, you know what it is? I think I'm not entirely sure, but because it's a see all of these. If we just go back to the main output. Jesus, sorry. Right, we run this again. There's a lot of zeros at the end, and this could be the cutoff that we were talking about before. So I'm thinking that if I run it backwards, the zeros will be down this end. So instead of getting like the high signal here and the low signal here, we'll get a high signal here and a low signal here. And then when you combine the two, you'll have two high signals. But that works fine for this data set. I'm sure it worked fine for all of them, actually. So that's my idea with the forwards and backwards. And then we could, it's plausible to work on the other part, maybe getting it more tightened up, but I'm not entirely sure how to do that. So that is a reduced intensity anomaly solution. Now, what is the combined reduced intensity anomaly solution?
Oh yeah.
Sorry for this. It's probably the same thing actually. So yeah.
You did that also?
Yeah.
Does it show the anomaly show up there?
I don't know. It's been a while. Oh, so combined might have. Oh, it's the discords. So there's the discords that we looked at. This is not my work. The Discord stuff is that guy Eamon Kyo. He's done some interesting research, Joe. Actually, he looks at discords in interesting things like bird calls and DNA. You know, so he's quite
genetics.
Good data sets. You know, interesting data sets. And music is another one he looks at, and just kind of fun stuff for popular audiences as well. Finding not just the discords within it, but also the motifs, like the repeat patterns, which is interesting from the point of view of studying birds and maybe animal language and stuff like that. So it looks like I've implemented the matrix profile here. And maybe that's, why would it be combined with a matrix profile? Sure. Why is that output so terribly long?
Does it show the graph? Does it plot the graph?
Well, I mean, we could run it and find out. I could try and run all of these. We might encounter an error at some point. Sometimes that happens, you know, if you leave your code for a while and maybe you've changed something, and then I don't think that's the case here. Might be a good idea to go a bit slow here and look at what's going on. So there's random variables. Then we basically copy it and paste it onto the end. So that's just the list is doubled. So we need that for the window size so that we can go outside of the window size when we're doing the sliding window, so that we don't get a cutoff. That's what this is doing then. It's the window size is 30 and segments, right. Mirror matrix over diag sort and take the nearest neighbor.
Prime factorization, things like that won't work here, right? Or the iSpace things that Christian is doing.
I don't think so. As for prime factorization, no, I haven't considered using it, to be honest with you. But do you have, like, is there some way that is used in these
random? I mean, to remove the random things.
Oh no, well, no, the random stuff is just test data.
No,
you know,
a lot of it is random, right? Almost like noise. But inside that, there's anomaly inside the random.
Oh, that's right. But the anomaly is kind of noise as well, in a way. I mean, anomalies are more like.
But it has a different pattern, signal pattern than the other
ones. Yeah.
Ones.
Okay, so sorted eye for eye and.
So you have to find the patterns. You have to. It's a pattern. Pattern analysis or pattern detection.
Yeah. Okay, we'll continue on. This might be. Did I already do this? No. Size K1. So this is kind of MP compute. So this looks like, now we're into the matrix profile. I think this was my own attempt at something here. Probably. There's the upward triangular matrix. Then we get Euclidean. So I think that's my version of just implementing the matrix profile, and then we get into the real deal. Kyo's work here, and then we get the outputs of Kyo's and his team. There it is there. And this was to show that basically, I think this basically shows that it kind of failed in a way to discover the anomalies in the right place. Oh, not to worry. We'll just ignore that error. This is going to run an error as well. So is that. Oh, that's not good. So many errors. Oh, well, we'll just keep going. Oh, no, actually, maybe this isn't good. So this is what I was talking about. Come back to something else. I suppose I'm just investigating here what's going on inside the matrix profile.
So all these are Discord scores?
Sequence and pairs. No, this was something else I was trying out. You see this looks like a thing I was attempting to do that's connected to this kind of thing, or more specifically this. See the way this goes? 5 by 4, and then 5 by, oh no, yeah, 5 by 4, then 5 by 3, then 2 by 5.
Reduce the matrix size. Reduction technique. Something
or sorry, actually, I got it wrong. It's 2 by 4, 3 by 3, 4 by 2. So they're inverting, you know?
Asymmetric. It's a symmetric matrix.
And then these ones are doing the same. So it's going 1, 7, but it ends at 7, 1. So I was just, I think I was trying to do that. Looking at that for some reason. I should really take better notes. Oh well. The last checkpoint was April 20th. It's not even that long ago, but it's amazing how much you forget. Slide. Okay. So this is just creating, attempting to create the constant matrix profile. So altering this kind of sliding window into this. That's what I'm attempting to do here. I think on a test data set, so this is like a toy version. Now, attempt to have exclusion zone. My version. All right, so I want to some sort of exclusion zone. I'm not sure if this was ever used properly. Ascending, descending numbers allows for quadratic dimensions for matrix. So that's what these were, ascending, descending numbers. So that gives quadratic dimensions. What do I mean by that? Great. Well, obviously, it's something to do with the quadratic curve, the kind of Gaussian curve. So we create the matrices.
I'll show you the matrix protocol I am doing. Maybe, I don't know whether it's applicable, but I change the axis. So you always get a, straight line, so that, you can always figure out outliers, things. I don't know whether you can, because you have to know the physics for that. And that may be a difficult thing. Once you know the physics, you can adjust the X and Y axis. And so you always get a straight line regression. And if it is not, then it's an anomaly type of thing, or outlier, things like that.
Okay. Well, the other thing, considering, I wonder what's going to happen here. There's an error. Why? What's the error? Yeah, you see, so when I was messing around with this before, I obviously changed some variable, just testing something out. And then I must have saved it with that altered variable. I think that's what's going on. Unless the problem occurs here, but I don't think so. Maybe. Okay, so this is not, but if you think about it, it's going to be random list. These are all going to throw errors, I think. Yeah.
So you are conducting data analytics, right? Or analysis.
Kind of, yeah. These are just this is just rough work down here, I think. So I'd have to go through that again, but so it seems like I'm combining matrix profile with.
Does it pull out? Does it show more? Is it able to separate that thing? That.
Well, if you go back here, it should. See, this is titled Combined Reduced Anomaly Solution, which I think is just, that's not this. That is like everything after this. So including that. Then we have what we're looking at there, upper matrix, constant matrix profile discords, and then reduced anomaly detection. So yeah, I think actually this is somehow the combined. Yeah.
So it shows a step in this case, light step.
Yes. Yeah. So it's combined because it's using the seed and this. Yeah. The difference. So it's combined in that sense. So that's That's why the end of this slide points to this notebook, reduced intensity anomaly solution, rather than combined reduced intensity anomaly. So that clears up that mystery. I hope that's does that make sense to you?
Yeah.
Okay, it makes sense to me now. There was some other point I was going to raise. I don't know if you're happy to move on. Was
This one, yeah, the radius thing.
I spelled that wrong.
Radius.
Dobrovolsky radius. It's obviously some Eastern European name.
Maybe. Are you also doing the processing of that?
Yeah, I used MATLAB to do it. You couldn't believe how difficult it is to process these. I think I might even have another slideshow that I show how bloody complicated it was. I wonder, is that here? Am I working on that? Yeah.
These are to find the regions, right? Where exactly it's occurring. Predicting the locations.
No, the Dobrovolsky radius graphs.
What region? What region?
It is the preparation zone of the earthquake. So if the epicenter is here at the center of the preparation zone, that's where the epicenter is.
But is it before or after the event? Is it post-analysis? Is it post-analysis?
It would technically be both before, after, and during the event. But it's called the preparation zone, so really it's talking about before. So it's trying to figure out how big is the preparation zone for this particular earthquake? Like how much of the
activity,
the fault lines, how much of them are involved? Like what length of fault line is involved?
It's very similar to corrosion, we call it occluded cell, like formation of pitting or crevice corrosion. It forms like a occluded cell. Something happens inside that, the chemical composition, the pH, everything changes. So it's kind of very similar. So you think, and then stresses will crack the thing. So this is very similar. So you are essentially like shifting, the thing is shifting, right? The
yes. The
continuous shift, what are called so that shifting causes cracking to occur.
Right, there's shear forces, and then the water leaks out of the ground into the cracks, and then that
the magma starts flowing into that thing.
Sorry, what?
Does it the magma, the inside?
Well, maybe, but they mentioned water, like the groundwater. And there's all sorts of things like liquefaction processes as well that go on in certain cases. But that's just a theory. The other competing theory is that the cracks are constantly, the Earth is constantly breaking and then reforming, and then it's just happening all over the place. And then there's finally some sort of event. But the main thing is that there's all these cracks happening within this region.
Is it connected with the petroleum? Does it have any correlation to the petroleum formation, things like that? The gas, oil and gas type of thing? Is it
we're not entirely sure how that is done. What is the current theory? It's to do with carboniferous life forms that kind of decay and are compressed in heat, and then...
So it produces some kind of a product in that process? So we can analyze the product?
Well, I mean, it's interesting. Well, I guess seismic would, seismic processes be involved in the creation?
Or even diamond, things like that. You could perform little diamond things.
Maybe.
Conversion of phase transitions.
That's plausible. But I think with there's another theory of, I've forgotten what it's called now, but the microbial theory of oil production, where it could be like some sort of bacteria down there that basically produces it as a byproduct for whatever it's doing. But
could be viruses, things like that also,
something along those lines. This was all my struggle trying to plot the Dobrovolsky radius. I was having terrible time of it. So, and I got this map somewhere, but this epicenter is wrong, and the whole method of openstreetmap.org was really frustrating and terrible. I also used Cartopy, PyProj, Geog, and GeoPandas.
There are too many variables.
Well, yeah, these are more. This is a plotting library. This is connected to that. It's mainly for plotting on the Earth. PyProj and Geog are like, they're also modules that are all about plotting on the surface of the Earth, essentially, and drawing circles. And then GeoPandas is like a big processing tool, very much like Pandas, but specifically designed for geographic coordinates.
Is there anything like with all the satellites, you have like a triangulation or something like that going on, right? You have.
Yeah, I was thinking about that from the point of view of figuring out where exactly the anomalies are coming from, triangulate between the satellites, different things like that. But she turned out to be like a very complicated process.
Yeah.
I think when things start getting very complicated, I think it's a good idea to back away from that.
Yeah, yeah.
That's not.
But how about you do first surface profiling and then do depth profiling? You do surface and keep going each depth all the way to, you know, the stratos. I mean, all the way down to magma level, the inner core. I mean, something like that. At the bottom of the sea, and then you say it's sea level. Then below the sea level, go each level, you know, and then above, you know, above slightly, but mostly you want below the sea level, like Mariana Trench, things like that are big things, right?
Right. Actually, that's a good point, Rajan. Now, I think in terms of attempting to predict earthquakes using satellite data from the ionosphere or whatever, or even the lithosphere core interaction, on all of those things, you can only really take data from on land or near the coast, anything that happens in the ocean, because the actual, interestingly enough, the electromagnetic field in the oceans is much stronger than it is on land.
Yeah.
Yeah, there's a guy who created some sort of metallic model of the Earth, and he had to use like a material over the oceans that was like 1.5 times more conductive or something before his model worked. So the oceans are, yeah, way more conductive. You see that all the time in graphs as well. So we have to leave them out. Yeah, so that's interesting though. So what you're talking about, taking a surface profile of the surface of the Earth, obviously, and then going down into the core.
Yeah, layer by layer, slowly go by layer by layer.
How would you do that though? Oh, through triangulation, is it?
So you have to do the one of them in the sea. You can do it. For land, it's more difficult. I mean, they have props that you know, like you have the core, right? You to take out the core, the ice core, you know, the center of the Earth, and they analyze the data in there.
Rajan, ice cores are what you drill from the Antarctic or the Arctic.
Yeah. But it's more difficult. Whereas you go to sea level,
core, like in the center of the Earth, would be like iron.
Yeah.
Is this some sort of magma?
Yeah.
I think is it made of iron? Molten
iron. I mean, it's a molten state of all the metals, mostly iron.
Uranium. It could be uranium down there, I suppose.
Yeah, I mean, there are nuclear things there, but mostly it is iron, I think.
Yeah, I think mostly you're right.
Yeah.
The whole thing is a molten
state.
Yeah, that's moving around and then generating these electric currents because it's
and then magnetic. It produces magnetic field. So if you look at the magnetic activity, I don't know how far you can resolve that. They produce magnetic activity. So if you look at that, maybe you get an idea of, I mean, it may be difficult, but how the magnetic activity changes with each layer, you know, because you have different compositions of iron or what they call the magnetic, you know, the magnetic iron versus non-magnetic iron. So at
Yeah.
some levels, magma it is forming basalt, things like that, different forms of rock formations,
Yeah.
and
And
some
so
of them are magnetic, some of them are non-magnetic. So how
so
they affect the magnetic lines, you know? So
yeah.
they actually break up the magnetic, homogeneity,
Mm.
and that can create the fault lines, So you can
Yeah.
produce the stresses, some stress, magnetostriction, you know, uh, events, So if you find the magnetostriction coefficients, things like that, if you are able to figure out that, you can say, okay, these lines, you know, you will have more magnetic action, the other lines will have less magnetic action. So layer by layer, and you have to
Mm.
continuously monitor them, of course,
No,
how
I
they
think you're right,
change.
because I mean that is exactly what the swarm constellation was designed to do. You see, you have this picture here is actually very
Uh-huh.
instructive for what is going on. You have two swarm A and swarm C are going in a polar orbit, so that's why they have the
Uh,
aurora borealis up here. They are going in a polar orbit, and they're only separated by a little bit, like
uh,
this. And then swarm B is going around in an equatorial orbit, and it's a good deal higher. I think
mm,
it's like 200 meters higher or something.
mm,
I think these are at 400 meters each, and so this would be 600, something like that.
mm.
Or I think that's right. So basically, what you've got is what they say here: a three-dimensional mapping of the Earth's magnetosphere to provide a better understanding of the separation between the
The
core and the
core.
lithospheric fields. So it's giving, like you say, a triangulation, but also I think a parallax view.
Oh
So they're
yeah,
getting like a perspective depth analysis
yeah.
into the magnetic field. So that is fascinating. That is not something that is part of my research so
Uh,
far, but it sounds really interesting and I would like to get into it. I'm just not sure if it's exactly relevant to the area of anomaly detection for,
mm.
oh, hang on a second. For what is the word for earthquake predictions? So, but it might be, but it just goes to show how complicated the whole thing is. If
Oh yeah.
so, for sure, it's pretty complicated. Oh yeah,
Do
so
you
that's
use
all.
the Brolsky, you know, radius, mostly the Brolsky circle or radius? Yeah.
Yeah, so this is all like the preparations. So the idea is
Preparations.
yeah, so the satellite flies over this area every once in a while, and so the idea is you collect the data from just inside the circle or in this
Mm.
square region,
Is
like
this the
approximately.
best technique so far? The Brolsky radius
Not
method?
really. I mean, so the satellite goes over, and you just detect the anomalies in this region up up to, like, that's what I showed, 7 months up to the Aegean Sea earthquake, and you detect all the anomalies that occur, and then um, and that's really it. That's the end of the research, then, because they're just trying to show how good their anomaly detection method is, whether it's able to detect anomalies in the data prior to the earthquake or not, in the electromagnetic data, that is, geomagnetic data. So yeah, that's it. I think so what I tried to do then was, later on in the research, I noticed that there was a Chinese group that did manage to predict an earthquake in China, and they actually used
Hmm.
all of the landmass of China. They didn't just focus on the one
Hmm.
tiny area where the earthquake might happen, and that's something that's useful to point out, is like, how could you possibly know where the earthquake is going to happen? If you already know where it's going to happen, then you've already predicted it in a sense anyway.
Yeah.
So
The
so it makes
preparation zone, you don't know. Yeah.
Yeah, exactly. You don't know where a preparation zone is, really, because then if you did, you might even know like how far into its preparation
Yeah.
cycle it is as well.
The
So.
different things are happening in different places, but
Yeah, I mean, you probably have an idea of a preparation zone, but you don't have an in-depth knowledge of what it really is, like how big it is, what the stresses are inside it. I don't think so. I've never heard of anything like that. So that's why I decided to use the entire Earth, and that's how I got my prediction, which obviously has a lot of noise in it, but so that could be just noise as well. So there's always that. Yeah, but I think this is definitely a better method. Like, you know, if you actually want to predict like earthquakes,
this is
you
a
should
combined you know
regime,
thing, the combined effect, the combined
reduce
anomaly detect reduced
anomaly.
CRI something.
No, because really, you don't really need the reduced intensity anomaly solution for this. You only kind of need to detect the spikes. You only really need the seed version. Sorry.
Seed.
Yeah.
So
Really, I
deep
think.
learning uses seed.
No, because seed uses KNN and the NumPy all close, and KNN is just and
It's not machine learning.
is machine learning, but so in order to predict, I used an artificial neural network. So I think a better option would be to use an LSTM in future. I did try to use an LSTM to predict the magnitudes, and I just got a lot of
neural network where you had the input, the hidden, and the output thing, kind of thing, right? That's the one. Is that a neural network?
Yes. This is a very good
that's
example.
Okay. Q learning. Q learning.
Q learning is different though.
Oh, this is DQ. Deep Q network. Something.
Right, which is just the you're just taking the Q table and putting it into the hidden layer of the neural network. So this is just
more analytical. So it's more in analytical type of thing.
Yeah, well, it's in a sense it's like it's a load of weights that are first randomly put in here, and then you see if you get the right output, and the error then, let's say this was meant to be 1 and this one is 0, but it's the other way around.
So the hidden thing is like a what you call in a diode. It's like a manipulator. I mean, you are trying to figure out what that is. So by using the rules, so it's adjusting those things. You can find the rules by which input and output comes.
Right. So I was saying it wrong actually, because I guess say if you're it depends on what you're doing, either classification or linear regression. But let's assume you had like a list of variables here, and then it's trying to predict each one as it goes down, and it could be a 1 or a 0, and it predicts here. It predicts 1 where it should have predicted 0. Then it's going to have a high error, and that's going to be back propagated into the hidden layer.
So it's like a feedback system that where you
and it constantly tries to reduce the error by doing this differential equation where it's moving downhill, basically a gradient descent, and then once it gets to the bottom of that gradient, it's at the minimum, the lowest error, and that means its prediction is supposed to be at the highest accuracy. So the loss.
So it's kind of a manipulating
or inverse.
It's like manipulating hidden variable type of thing.
Yeah, must be. Yeah, that sounds about right.
So manipulation of hidden variables type of thing. Okay.
Yeah. Is there anything else that I was trying to get across with this?
Yeah, I think.
Lebowski radius and noise. Well, I mean, really, when we,
I can show you the thing. Once you are done with that, I can show you briefly, and then I think we'll be.
Yeah, I think we're done.
What I was talking about earlier.
Yeah. There's only one other thing, but I'll look for it later. I'll just stop sharing now.
So should I go ahead and pull up that?
Yeah, I do. Yeah.
Okay. So let me. What I recently, like last time, I have shown. Let me see. trying to pull out first. So can you
see?
Yeah.
Oh yes. I need to add this to stream, is it?
Yeah. Can you
Yes.
see that now?
Yes.
Okay.
Okay, so you're
So
doing turbulent distortion tensor gauge fields.
yeah. So what I am trying to do is I am trying to sketch something that will show.
Yeah.
Okay, let me see.
They're a little bit sketchy.
Yeah. I mean, I just sketched out only
Yes.
recently. You have to do some more processing.
You might be able to find, if you could go online, could you find like, and just type in turbulence, probably get something that would fit your aims closer.
Yeah, we have to combine somehow because you have the thing. I don't have much of this thing.
But you could like literally just type it into some sort of search engine, image search for turbulent flows.
So if I move this, can you see this one?
Yeah.
Does it move there? Because I cannot see. Okay. So I'll just concentrate here because I cannot see the screen and the thing at the same time. So what I showed you last time is, yeah, last time Christian was here, is this one, right?
Yeah.
Yeah, you remember that, right?
That looks good.
And then I went there and then look at the what is happening more fundamental level. So I backtracking to the superluminous thing. So this is supposed to be a superluminous thing, the magnetic thing all over the place, like a turbulent, superfluid. I should put superfluid probably here, like superfluid.
Yeah.
Or superfluid like. So it's like superfluid like, right? So what is happening is that, so in that one somewhere the local see what I'm saying is that if it's magnetic, it has some vectors all over the place, right? So it's random. So the vectors are like monopole vectors, with I would say like having monopole vectors.
Okay.
Okay. Randomly. Something like that. So it's randomly, it's all over the place. But within that, at some point in the fluctuation, any random situation, there is also a situation where it starts to align itself. It starts to align. So the vectors start aligning with each other, particularly because you have the north. This is the north and south monopoles all over the place. And we discussed and Christian agreed that actually there's a way we can actually prove that get separated because the speeds are very large. So you have the information wave versus the light wave. So it separates the light wave. It's too fast. It's superluminous, faster than speed of light. So it separates the vortex, the vortex up, the south pole and the north pole apart. But at some point they come together, and because the north and south has attraction on trying to form dipole type of thing like Horde, so then it starts aligning itself at some point. And this is something we can prove, I think, even mathematically, but it requires more detailed.
I think when you were saying about the north and the south monopole align, when they align and come back together, they will form the torus that
Manuel, form torus type of thing, exactly.
Which is very different to it's very different topology and structure to a HOD, which is like a flat disk in
Yeah.
John's research.
So at
But
quantum level, yeah, actually that
yeah.
may be sub-quantum level. So at quantum level, right?
Mm-hmm.
At
Well,
quantum level, probably may form, may create Horn torus.
right. So when you're saying quantum level, you mean subluminous? Do you? Or couldn't those particles be
Yeah.
traveling?
So now Horn torus at the vacuum. So so what I'm saying is that now this is superluminous, right? Now
Okay.
this is coming when this forms comes closer to vacuum level. So here it's the vacuum level, and then you have the. So I will show the vacuum level here if I can draw this. I don't know whether I can try to draw something here.
Could like is there like you could have a particle in the vacuum moving at the speed of light? Could you?
Yeah. So you can have, if it creates a
Oh,
vacuum level here, right?
yeah. Yeah, I see what you mean.
So
Sorry.
if we can
That
write,
makes sense. Yeah, I
I
see.
can.
Yeah, I was just getting confused there. Yeah, that's what's that works. So yeah, so it wouldn't be at quantum level because I mean, couldn't you have a quantum within the super luminous? We're already at the
Yeah.
quantum. Excuse me.
Oh, I don't know whether. So I'm saying to see vacuum somewhere here, but I had to put it down. But I'm saying that it creates vacuum somewhere here, and then above that you have the.
What's above that?
So this is the vacuum level. Let's say this is the vacuum level, right? So then above that you have the subluminar matter phase. So you have, you see what I'm saying? So this is the
Yeah.
superluminar thing, right?
Yeah. So it's like these three different
layers.
Yeah. It's like the three different worlds of in Hinduism, isn't there?
Yeah. So this is the superluminous thing.
You have to pierce through the three worlds. Do you know this? Yeah. There's the celestial sphere, and then there's is it the human sphere? And then the animal sphere? Or no, the physical, spiritual, celestial sphere. I think that's it.
Superluminous phase, let's say.
So yeah, you can have these three different levels, and so the ones at the top are moving the fastest, and then below that, sort of slower.
So these are superluminous thing. I have to adjust this thing. But then you are above that vacuum, because the distortion creates, these things are now arranged, right? They get aligned and they form magnetic thing, and then it can form a light, a boson thing in the vacuum level, and then because it separates, once it separates the superluminous, the vacuum separates the superluminous thing. Now this can escape, like in the condensate I was saying, can escape into these higher level above the vacuum, so to say, and it forms subluminar matter phase, inertial subluminar, let's say it's inertial subluminar matter phase it forms. So so this is the three possibilities. What I'm saying is that this is like your thing, like anomaly, within the superluminous thing. The distortion is like an anomaly. So if you can pick up that anomaly somehow, that shows, that's where you can, what I say is that's where you have the hot PDP like mechanism. It's very similar to Higgs mechanism, but in this case, hot PDP mechanism operating here, and that is preparation stage to produce the like inversion, pinch off, and inversion. So it's produce an inversion layer, and then it pinches off, producing particle. Uh, a particle
Well,
that
actually,
goes.
yeah.
To,
Rasha, I had
so
an idea. Sort of remember back in the day when we were talking about the 24 cell.
uh-huh,
I was working on trying to expand it into the 600 cell,
uh-huh,
and then expanding that into the 120 cell, and then you can what you can do then, right? You have the 120 cell, which is a load of dodecahedrons in 4D space,
mhm,
but it's a three-dimensional. It's not a hyperbolic four-dimensional space. But you can
uh-huh,
extend it into becoming, so it can become hyperbolic, which means you can have four right angle right angles. No, sorry, five right angles in a 360-degree rotation. Yeah. So then we have four instead of having three dodecahedrons connected
mm,
together at each vertices. You have four. So
mm,
so then you can you can tile space with that in a
mm,
hyperbolic sense, which is kind of cool because you could think of it as like maybe connecting with relativity, but that's kind of three-dimensional space is like usually represented as a flat plane, and then time goes up. So
mm,
a little bit, maybe too many dimensions. But so what we can do is we can start reducing them down, and you can alter all of the dodecahedrons into grids, like squares. So then it
mhm,
becomes a big grid that goes into infinity in all directions, and then you can take the axes of those squares. So some are green, like the x-axes that's there are green, the y ones are blue, and the z ones are red. And then you can a bit like what Christian was talking about, where you kind of you start folding the sides of the cube together on each side and on every side until they form like these six rings that
mm,
are orientated a bit like the Poincare sphere,
mm,
the block sphere, where you have the x, y, and z axes, but they're these rings. And then, so once you do that, you could have like, you could start interpreting things like on a deep level. So instead of expanding into like relativity, where instead of contracting like all of this hyperbolic four-dimensional space, shrinking it all down just into this tiny little thing with three rings, yeah. What the heck is that? Is that not the PDP circuit? Is that not like
yeah,
total energy production? Complete like, and it contains everything in it as well. It's got elements of the Riemann sphere, I guess, six
mm,
subdimensions. So you could have like one ring could be red, one ring could be green, one ring can be blue, as I said. So they can be the three color charges. And then each ring intersects each other ring at 6 points, which are, kind of like octahedral geometry. So those 6 points then could be what? Well, you could have them as 6 of the 8 gluons, because two gluons are usually aligned anyway. So they could be factored out at each rotation. That wouldn't be a problem. But you also have the 6 elements of the electromagnetic force, don't you? E1, E2, E3, M1, M2, M3. So they'd be the directions in differential space, sort of the field. So they could. So you see what I'm saying? So we could like you kind of create a structure of everything, but in this small. So it's like a machine like a
mhm,
computer that encodes things, you know. And then along the
yeah,
outside of each ring is one of those matrices from the um, from the 24 cell, which each one encodes a different particle. So that's why when they intersect, they'll line up with all the gluons, for example. So red gluon with blue other gluon, so like G1 and G2, and then so on. And then you could have the three rings could be of different sizes as well, because they all have to fit into each other. So that's where you get the three families of particles. The heavier ones are inside, you know, the smaller radius with a higher frequency, so they're heavier and they go out. And yeah, there's a couple of other things there. You've got, so because of the 48 matrices, let me see if I'm getting this right. Since you have 48 matrices on each ring, that would be 48 by 3, which I think is 144. But let's say it's 24 then. So you have like 24 fermions on the outer ring, 24 bosons in the inner ring, and then 24 fermions again of a different kind, maybe left-handed, on the inner ring. And then, so that's 72, which connects back to E6. So then you could have, you know, the E6, which I think is some sort of grand unified field theory uses E6 because it's unbalanced or something. It's interesting. I'd have to look into it. And then +1 from somewhere. I suppose the central axis point is a star, so like kind of like a very intense, highly energetic object, which is like dark matter. And then, so that thing 72 + 1, that's encoded in a lot of places, like to do with the stars. The what's that thing called? You know, basically the star map around us, which is which can be distorted using the same matrices when traveling at the speed of light. So I forgot what they call that, the background or something, star background. So yeah, I'm just thinking like those rings could be made of tachyons, you know, like faster than, they'd be way out at the infinity points of the hyperbolic space. So when you contract it all down, all you could be left with is like tachyons, and they become a finite ring. So and quantum in the Bromian rings. Oh yeah, there's also other stuff to do with the dot product. And so I think this thing, the rings are tachyons, rings are continuous, but matrices make it quantized. So that's the idea. Like when there's two matrices, you can't have like half a matrix joined up with half another. They have to slot together perfectly. You know the way they have to be right size. So that would make it kind of quantized in a sense. So we have color charge with all the electromagnetism. Gravity would be in there because the 8 gluons and the 8 gravitons are symmetric in this model. Strong force, weak force. Not sure about the weak force is in there, obviously. And we don't have the Higgs though. But yeah, there was something else there about. Yeah, because you remember you were saying a while ago that it would be interesting to do a modeling of the torus moving in 4D space. It would be rotating, spinning, and inverting and all that stuff. Yeah, I think that's a really interesting concept. Like, you know, if I could get a 4-dimensional model of Emmanuel's horn torus, if I could figure out how to make that in the first place, which maybe might not be that difficult to do, but and then we could like rotate it in the 4th dimension while rotating it in the 3rd, and a couple of like do those Clifford rotations, you know, that. So it's like a gear thing, and see what comes out of it. It could be really interesting. What do you think?
Yeah, so we will be able to do that. I will write up this one, and then maybe publish a small paper if possible. Then we can add your thing, you know, all these, and you are talking about now with the 24 cell, 48 cell, and that analysis, you include that, and then say how, because you have in discussion with Emmanuel, you talked about how the geometry you can explain the superluminous thing, right?
Yeah.
So that kind of, you can explain from geometry how the superluminous can happen, and you can explain in terms of specifically in terms of 48 cell and then 24 cell, and then you come up with that contourus thing, and then the 4-dimensional, the Cottonians or whatever, the contourus, the 4-dimensional thing, and you show that, yeah, how they rotate and they become very similar. So we are approaching from two different methods, but they two coincide. So that shows that there is geometry. We are showing one aspect from geometry, one aspect from the mechanism. So we combine the two. We see that, yeah, how the quantization occurs.
So are you
that will
saying
be
that
a
when
really.
you have a PDP circuit, it isn't is it the same as Emmanuel's model, just from a different point of
No,
view?
actually,
Oh,
it's not. By manual, it's the next level. PDP is more sub-quantum level. Emmanuel's is closer to quantum level. So
oh yeah, of
PDP
course.
is,
Yeah.
see,
Well, I
PDP
could,
is more
yeah,
deeper micro scale,
yeah.
closer to Planck level.
I could probably do like a 4-dimensional version of Emmanuel's thing, but using the rotations that you were suggesting.
Yeah,
It'd be interesting to see what would. But I mean, that would just be purely a difficult thing to do. So like worth trying, but on another level, it might not be so needed, But what I have found, yeah, I've got some kind of cool research in that area that could be good. I don't know if I
yeah.
want to do too much
What
before
we
I.
had to prove that the superluminous thing, it's not. We can prove it from a geometry point of view, from mechanics point of view. The superluminous thing is a real thing, and
Well, this
it's
is
quite.
it. I think because remember I produced not this presentation or the last one, which was Christian's, but the one before that with the neural network imputation of galactic.
Oh yeah.
Well, based on that, it showed showed that the Earth is inhomogeneous. Oh no, sorry,
Yeah.
the universe is homogeneous, and also isotropic, or yeah. So because of the axis of evil situation.
Oh yeah.
All of which seems to suggest that the Earth may be sort of in the center, which is why everything looks like it's expanding away from us, and which is true from the point of view of relativity anyway, because as Sungenis points out, if everything is rotating around, if the Earth is rotating and everything appears to be going around the Earth, then you can just reverse it, and that works as well in relativity. And obviously, there's a couple of things you could say about that, but ultimately, the logic works out. Depending on which reference frame you choose, it's still correct. So, but let's say that reference frame wasn't just like an arbitrary choice, but was actually the choice. Then what he's saying is that, like, once you get outside even out to the orbit of Jupiter, that's all moving at the speed of light, I think, at that distance. But because space, like the ether, is then under tension because of the spinning, the orbital angular momentum, it gets more tense, and so light travels faster out there. So when you got out there, you wouldn't notice any time difference at all. So it's very clever. I don't know if Sungenis came up with that, but it's pretty good.
Combined with Penrose tiling and everything we were talking about last time. Penrose tiling, if it moves along the surface of the Penrose tile.
Oh yeah,
then
that
it
was
can
very
move
good. Yeah,
much faster.
I do like that. That's also a brilliant idea. Like, if you have a central point in the universe, and then everything grows out of that like a cell, like a crystal cell structure, that's exactly what a Penrose tiling does. It never repeats. So you could have like an infinite universe that goes on, kind of thing, that never repeats. So, and it could be like kind of frozen out or something in a sense. Crystalline, but
on the surface it can be superluminous, right?
It would be 4-dimensional, because the Penrose tiling, if I'm not mistaken, is a type of a view on a 600 cell, which is or
yeah, if we can connect all that, that will be fantastic. In that paper, we can write.
Oh yeah, great. The you know those quasi crystal things that Penrose predicted using his tilings, order 5 symmetry or something like that, and
the fifth dimension type of thing.
Quasi crystals, and yeah, then they were discovered. And if you look at those, I mean, those are clearly 4 or 3D projections of 4D shapes. You know, that's quite obvious. So, and also they are projections of cells within the 600 cell. So therefore, space, if we were to go with this theory that space is the geometry of a 600 cell expanding out in all directions, infinitely and uniquely in all directions, then yeah, it would imply then that space is a 4-dimensional projection or a real thing, which would go to, how do we say, to confirm or, like, you know, bolster my argument that everything on the quantum level or in the universe is kind of 4-dimensional, because I've used it to explain a lot of things at this point. I've used it to explain quantum chromodynamics, like how the color changes occur. Well, that was it within the 24 cell, but it's a nice model anyway, even if it's not. You know, it might be true, but it's a nice model. Do you know what else? You know, I got a lot of things though that out of the 4-dimensional thing, like you're saying, superluminal speeds of particles. That's in there. There's a lot of other stuff. Oh yeah, I'm thinking polarization of electromagnetic light is also a 4-dimensional transformation, which is fascinating because that means that the interaction between electromagnetism and matter is somehow 4-dimensional rotation.
The gravity coming into picture, right? The gravity.
I guess. Jeez, I haven't really thought about gravity and how it would come into the picture. Interesting though.
The graviton or something comes there.
I mean, I guess, yeah, it could be. Yeah, it could be in there in terms of the 4 points or the eight vertices of, like, let's say the hypercube. Let's say we're using that as the model. If we're using, if we're using the 600 cell, that's another matter altogether. It'd be more complicated. But I don't use that. I would use the hypercube because it's easier. And in that, there's so there's a left-handed, you know what I'm talking about, wave, electromagnetic wave, and then outside of that, in the 4th dimension, like surrounding the entire hypercube, is another wave that also looks identical. So it's also, but because it's in the 4th dimension, it's actually going the opposite way. So it's actually a right-handed wave. But when you rotate that in, the left-handed wave in the center goes out, and the outer one goes in, and then it rotates. Also, I think you have to rotate it 90 degrees. So it's a Clifford rotation as well, possibly. Yeah, it is. It's a Clifford rotation. It's the only way it works. And then, so what comes in the center then is a right-handed wave, which is how. And then this all relates to Bell's inequality theorem. So, yeah. So like the reason why, you know, there's no hidden variables, but there is.
I mean, locality or non-locality.
Yeah, I heard a guy. There's actually, remember that Demystify Psi podcast I was talking about? There's a guy on that who is I think he's a famous. His name's Mead. He's a possibly very reputable electrical engineer who also worked in physics and between the two, and he was giving out loads, I think, about Bell's inequality that he was saying, and he was describing it as some sort of experiment that looked at non-locality to do with. So you have an atom emitting a frequency, a photon, and then it goes through a beam splitter, and then I think it's a beam splitter, and then you pick it up on either end, and whether it is, I don't think it was whether it's spinning, but it's polarity. Polarity of the beam is always the same. But as far as my understanding, the Bell's inequality is usually linked to polarization of light. So you have a polarizer that's like this, and then you have one like this, and so only 50%.
Plane polarization. Is that plane polarization?
Yes. Yeah. So the wave comes out in a plane, like a straight line. So then you have one at an angle of 40 degrees, and if you put that one in between the two, it's brighter, yeah. And so more light is getting through than otherwise would. I think you can put it at 90 degrees, a 90-degree angle, no light is getting through. But then when you put one in between those, this one and this one,
it's like phase angle.
45 degrees, then you get light through. Or else if you have one at 45 and one at 0 degrees angle, and you put one at 22.5 just in between, you'll get more light out than you were getting out previously. So the question is, how
magic angle or something? Magic angle.
It's not the magic angle though. That was something else, wasn't it? That's 52. You were talking about that, or Emmanuel was, and it's in his.
Probably Emmanuel, yeah.
Right, it's in his porn tours thing, which is nice. But no, this is not a magic angle because it's any angle that's in between.
Oh.
Yeah, and so you're expecting. Let's say if 100% is coming through when it's like this, and 50% is coming through when it's a 45-degree angle, then you'll expect 75% to come through at a 22.
Oh, in between.
But instead, 85% comes through.
Ah.
So why is that? And I'm saying that with the left-handed wave, that's got more. It's got more surface area. Let's put it that way. It's longer, you know, because it takes longer to go around than a purely sine wave. Not a planar wave, but in a sense, sine wave is just much. It has less surface area because it lacks the third dimension. So once you take the left-handed wave and start rotating it, it becomes the flat sine wave. And so in the process of polarization, you are either rotating the flat wave that's coming through the 0-degree polarization into a more left-handed wave, which increases the angle. But it increases the light that's going to come through, because like in the Poincare sphere, you have horizontal, and you have vertical, and then you have the diagonal and anti-diagonal angles. But all of that is happening within a 90-degree turn. It looks like a full circle, but it's only a 90-degree turn. So within a 45-degree turn, then you're no longer in that. Well, actually, the full sphere has another side to it, which has the right and the left. So instead of going just down one side of the sphere, you're curving around to the opposite side of the sphere and then down. So it's like this S shape, which is perfect. And the fact that takes much longer is why there's more light, I think. It's also an extra.
Is it connected with chirality in any ways? Like chirality, parity, that type of thing?
Well, you have the chirality of the light wave.
Left-handed.
It can either be right-handed or left-handed, you know. But that chirality is based on the rotation, because there's there's always a wave outside in the fourth dimension. There's always a wave on the inside. So when you rotate
mirror,
it flips.
like a mirror reflection type of thing.
Kind of thing, yeah. But it's a weird mirror reflection that would it work?
Mirror reflection is actually planar. So this will be.
I don't think it is a mirror. It's a weird one because yeah, it's a mirror reflection.
Mirror is more planar reflection.
I think like mirror. in three, if the two waves are in 3D space, they are mirror reflections. But if you copy, or if you were to compare the 3D space one with the 3D wave that's in the 4D space area, which has 3D in it as well, they will look identical. So there is only one wave in that sense. There is no such thing as a right-handed wave. You know, that might be why there is no, why the weak force doesn't bind, although that's that slightly separate issue. But maybe there's some reason why there's, yeah. Anyway, but I think from the point of view of the other side, they would see that as a right-handed wave maybe. So then there's only right-handed waves. So from the perspective of this other dimension, the fourth dimension, only right-handed matter will bind with the weak force would be the, that's come up a lot in my research. So there seems to be this other world that's like the mirror image of ours, where, you know, it's like left-handed antimatter and right-handed matter that binds to the weak force and not the other way around. That's correct. In this universe, it's left-handed matter and right-handed antimatter. Anyway, so let's say it is. Either that or we're in the mirror universe now. Oh my God. Get me out of here. Lord, weak spin groups. Right, yeah, these are all the things that can be covered. So the 600 cell thing could be interesting. And then if we could transform that into the 120 hyperbolic cell and then collapse it all down into this very compact thing. And I wonder, at that point, does the PDP circuit, is that where the PDP circuit is?
Yeah, if we can prove that, maybe you have to do the calculation or simulate, whatever you have to do.
Well, because you have a point in the center that's like it's a very intense something, you know? It's like really intense, whatever.
Yeah, intense thing. High energy thing. It's a high energy.
Then we're going to have the gradient out from that. And then you're going to have the 6 rings that rotate around in all these different directions. And then, so then you're going to have the curl, right? And the,
the vortex.
The vortex.
Yeah.
So what about that?
Vortex is like a curl, yeah.
Right. And each one could be taken separately because it'll be rotating this way and it'll be rotating that way.
That way, yeah.
And then you have the gradient. So, and then you have 3 more of those. So
that's what I think. What happens? I didn't mention that, but I think I want to add that.
Sorry, Rajan, I meant 2 more, 3 in total. Yeah.
Oh,
go ahead.
Okay.
Yeah. What do you think?
So what I'm saying is that what happens is that when it rotates like that, like I said, it separates to gradient and vortex, right? But it's at an angle, it starts processing, you know, like processing, like Thomas processing, like tactile thing. That is the one that stabilizes that. The processing will, like a top, it stabilizes. That's how it forms a particle, like electron or positrons, because it starts processing, it stabilizes that particular
local action,
local cell.
Yeah, what I'm going to go for here is that, like, the PDP circuit is not, in a sense, it's all particles, or like maybe this is just part of the system that I'm talking about.
Yeah,
you know, it has to be, like, because it's got all the elements. It's got the gradient, the vortex, and then spin and all of that. So it has to be part of the system I'm talking about. So but I'm thinking that this system, whatever it is, can create the particles. But it's like if you were to fold the entire universe, it would create this like thing. And this thing then is able to, when it's doing its thing, it's like projecting the entire universe back out, kind of. Oh yeah, so could be interesting.
Yeah, the mechanism by which
It'd be
that's
like
where
it's
I
like an
think,
engine that generates particles, but
yeah, like engine, where does it
because
come? Yeah,
inside of it, it is already infinite because the rings are kind of like tachons in a sense. They already extend out to space. They just look like they're very localized, you know, like in rings in a sense. So like all of space is sort of curved around them and squashed into them and folded. It's pretty
so
crazy
what I,
idea.
yeah, the idea is there are two lines of thought, right? One is a charge that Christian Gerd says, everything is charge. And then finally, gravity, everything is based on charge. But what we are saying is that everything is based on magnetic thing, like monopoles. Because
Oh, yeah.
you cannot have this high energy with the charge. That's my point. You need the very high energy. The monopoles have that high energy. They have, when you separate the poles into monopoles, they have very high energy. The energy is too very, very high. The energy density, what I mean is,
And why do you
but
need this high energy? Does it help with
to
the vacuum
produce,
capacity?
yeah, the PDP circuit, to produce the particle, you need this high energy
Oh, I
from
see.
the superluminous. So the locally, it should have a very high spike in the energy density to produce the particle. That's what distortion does. The distortion is essentially by aligning these vectors, right? The
Yeah.
monopole vectors, now it creates a situation when it's random, it doesn't, energy is all dissipated, you know, and but it is when it's aligned, the energy is highly constant. So you have very high energy density locally. That
Hmm.
creates that mechanism, like hot PDP mechanism to create the particle,
Yeah, that makes sense. So you have like some sort of the vortex, and then
yeah,
at the center or whatever, it's getting very
and the processing, and it
and then
starts processing and all that.
bam, the thing just bursts into life. Just kind of thing. Up it
Yeah,
goes.
then it creates, stabilizes that, and
Hmm.
goes into the vacuum phase. That's why you see particles popping out in the vacuum, so it makes
Yeah.
sense. So it pops out into the vacuum, and from
Yeah.
vacuum then it goes into the subluminar phase, where it forms the matter. The particles coalesce, and you have the, small big bangs. It's probably not everywhere it's occurring, so it creates the galaxies and all that, everywhere, and the stars. You have
Yeah.
all
Why
this.
not? I mean, it's as crazy. It's about as it's probably less crazy than what I'm talking about.
Yeah, it's a complete theory, I think. I mean, with this one, you can create more complete theory of
Yeah, I think
granulified theory of what.
it's difficult to prove it though, isn't it? So,
Yeah, you have to prove different things. Like your thing will prove about superluminous. The geometric aspect is quite important to prove the superluminous thing. Uh, you mentioned with Emmanuel about the geometry, how the,
yeah,
planar geometry, and how the Riemann, how it spreads out. Then if it goes on the surface, then it can become superluminous because of the geometry effect. You know, uh,
yes,
and then we can combine with the Penrose thing and your 600 cells, all those things. That then it proves about the superluminous thing, how the superluminous thing comes about. And once you have that, then we can show how the locally it can, distort because of the monopole. The vectors are aligned everywhere, but at some levels it can align themselves, so then it can form the, locally very high energy density to produce the particles, essentially.
right. Yeah, I mean, it's an interesting one.
So it's very similar to Higgs mechanism, but it's more detailed in the subquantum level in terms of. And I showed you about the Planck sheets and the vortexes, how they can, and also unified. So another thing I was thinking about that is that there are four types of fields. I will call them in general as convolute field, deconvolute field, then you have the gradient field, then you have vortex field.
And why
So
do you call it the convolution field? Is it a dot product or something? Convolution
yeah,
field.
convolute is a, like I said, Yeah, the Planck sheet and this one combined together and it forms a unified field. And in anomalous medium, it can be superfluous because of the phase velocity, group velocity type of thing. Group velocity can be
Sorry,
greater than
sorry,
the.
say that again, Moshan. I was a bit distracted. The
Oh, okay.
phase in the sheet, you know, the sheet.
Yeah, the phase velocity of the sheet
Yeah.
will be like a light. It's very similar to speed of light. Whereas
Okay.
the phase velocity of the vortex thing is very close to that of sound.
Uh,
Speed of sound. But when you
oh yeah,
combine them,
that was the other thing. That part of your research is this to do with the Raman
yeah,
spectroscopy.
Raman, yeah, yeah.
I can't say that word.
How the
Anyway, you know what I'm talking about. But so with that spectroscopic method, yeah, they fire the photon or the laser
yeah,
light at the material molecule, and
yeah,
it goes into the molecule, and when it comes out the other end, it can either be accelerated or, well,
yeah,
shifted or retarded in a sense. I
yes,
don't know.
exactly,
Yes.
yeah,
So, and the reason why that happens is because of the vibration of the molecule.
yes,
So if the molecule is stretching, it'll stretch the light, and if
yeah,
it's contracting at that moment,
exactly,
it'll contract the light. So
yes,
then that is a sound phonon thing kind of
yeah.
thing in
It's a
the
combination. It's combining the thing and
But how do you know? Because you're saying that the light turns into the sound and then turns back into light, which is
no,
a
no,
really
the
cool.
light and sound combine together and they
Yeah,
form a unified field.
yeah, that makes sense, doesn't it?
Yeah, yeah.
And that's
That's
what
what
you.
convolute. That's what the convolute field is. But the deconvolute is opposite to that. But the thing is that the
Cool.
interesting thing I found is that in heat, you have the convolute thing. I think yeah, you have the convolute thing, but you don't have the deconvolute thing in the heat.
Wow. Is that why it's
Because
linear?
yeah, in the sense that the you have heat transfer, there are three things, right? Conduction, convection, and radiation, right?
Yeah.
So the radiation is like our light or it's like light or the gradient field, whereas the convection is like the vortex field, right? And the uh, the conduction is a combination. It's actually a convolute. It's actually a combination of the two, actually, depending on.
Oh, yeah.
So but you don't
So
have deconvolution.
you have the convection is what?
Convection is convection currents. They produce currents like in the ocean or in the air.
Yeah, I know
Uh,
them. But
any fluids, any fluids.
what is that? That is a convolute one, or
No,
is
no,
that a
that's
mixture?
a vortex.
That's a
That would be the
vortex.
vortex field, like sound, very similar to sound.
Okay, and then the next one is conduction, is it?
Yeah, conduction. Conduction has both together, both the sound and the light together.
Okay. Conduction is sound and light, and the vortex is just sound.
Yeah, the convection. Yeah,
Sorry, the convection, yeah. And then what's the third one?
radiation.
Which is just light,
Light.
of course. Interesting.
A gradient. It's a gradient field. So we can now we are in a position to really understand. I think generalize to a gamification. Why heat? Like when we send light through like double slit things like that. When you have an object, it makes when it goes through an object, it converts into a heat. Now it has the three fields, but it doesn't have the fourth one, the deconvolute thing, right? But when it comes to the other side, the air, then it can deconvolute. It will have deconvolute field, and that's why. And then combining with the other one, it can produce a diffraction or interference pattern. That's my overall thing. Why it produces sometimes the diffraction? Why it produces sometimes the interference pattern? I think you can explain based on this.
All right. Yeah.
So that's what I'm trying to. I think the right now I don't think there's a really good explanation of why sometimes like even John was going through it, he explained some of it, but I think there are some he had the problem with the heat. He said he couldn't solve the problem of heat and the other one. He had gone up to that level, but I think now you need this 4-vector field matrix where it shows the convolute, deconvolute, gradient, and the vortex thing. That can explain, I think, all these things. So it's much closer to granulification aspect, granulified field theory type of thing.
Well, yeah, it reminds me of like it's very mathematical, isn't it? It's like
Yeah,
reminds
it's
me of
it's not an abstract thing, but I think you can show with blank sheets. We can sketch it out, and we can actually show in real, in the mesoscopic levels how they can occur, because the heat. What is heat? People are not. So heat actually has the 3 components, but not the 4th component. So that's entropic.
right.
So
Yeah.
when you go that, heat is like entropy, right? So if you go to superluminous thing, you can explain again entropic versus energetic thing. So superluminous thing could be like it may have entropic, all these 3, but at the local level it has the 4th one, the deconvolute one, which produces the energy. The deconvolution, what it does is it separates the field, like a Helmholtz decomposition, into a gradient field and a vortex field, and then it aligns that alignment produces very high energy density at the local level. That high energy density then is the reason with the hot PDP mechanism operating creates the particles, because the particles need that high energy. So it's a condensed, and then once it gets the high energy, it escapes into the vacuum, into the sublunar phase, where it combines and forms the matter. So it all makes sequential algorithmic sense, that we are combining one step at a time, stepwise thing. We are able to explain how each process is happening, all the way from subquantum level to the mesoscopic level kind of thing.
Yeah, interesting. Yeah, I mean, it is interesting. It's like you have this 4-vector matrix, and then like one of the terms drops out or is unavailable, a bit like in So and so that would be, sorry, was it heat is vortex, light, and deconvolution, is it?
Yeah, no, not deconvolute. Vortex, gradient, and the curl, or the vortex is the curl. The vortex, let me say, the curl, gradient, and the convolute in a more abstract sense.
So it can't deconvolute back into
the heat cannot do that. Heat does not have enough energy to do that. You need energy.
That is why it is, there's entropy and the linear.
The entropy is act like sink. Now you can go back to sourcing mechanism, right? So this entropy then acts like a sink. So it is always looking for energy for it to resurrect that, right? So the sink, so the energy source has a deconvolute, and the deconvolute thing supplies eventually the energy for the entropy, right? And creates that loop, the feedback loop with the sourcing mechanism, like even John is saying, very similar. But the heat is lacking that the fourth vector, the field vector. So that makes sense, because I want to see the Occam's razor type of thing, explanation, and the simplest possible thing. I think this one explains, even high school students, we can explain these things. And, that's why I look at it when I teach at school, that it has to make sense to them. So it has to be simple enough. But I think simplest explanation probably is the best explanation, according to me.
Well, I've been listening to you talk about this for 2 years, and it's been I am getting it now, though.
Yeah. So I'm trying to reduce each time, without losing the what I call the gumption, or without losing the, you are not assuming things. I don't want to assume like, oh, light speed should be constant, things like that. To avoid that assumption, you need extra work. You have to do extra work. So you just in the realm of things without
Yeah.
assuming things. If you assume, then you have to validate that assumption. Otherwise you can easily falsify that assumption, right? Always, like Einstein thing. That's why people are trying to falsify that. You cannot have, you cannot say speed of light is constant, things like that, and also the other aspects. So, but he's looking at the time dilation, but it could be that the speed is changing, instead of time changing, because speed and space and time are interlinked. So, it's the velocity that's changing. It's not the time itself, but the time is, if its time is quantized, like we mentioned last time, then that throws, another screwball in the middle, so to say. So that's where the problem came from. How do you time reversal and things like that, and the quantum aspect come into picture right there. And quantum says it's the event, not the time. You know, so that's where the whole confusion of catastrophe came into picture, the vacuum and the ultraviolet
Hmm.
catastrophe, and it
Okay.
threw the physics out of the ballpark.
Yeah.
The
Yeah.
catastrophe, and then people start losing faith in the physics. But I think now with these, I think it'll bring back the faith of physics. In the sense that physics can explain it, but if we use very carefully, how these are happening, I think we can explain. Like I was saying in this one, let me, I think somewhere here showing. We try to pull up that recently, very recently.
Wait a second. Yeah, yeah, keep going. But I was gonna ask a question about so radiation is light. Does it
Yeah.
also have? It obviously has the vortex, the convolute, and the deconvolute as well. Does it? Is that why it can interfere, like in light? Or
I mean, the heat does not have the deconvolute.
no, I'm talking about radiation though. Oh, but
Radiation, no,
is it?
radiation just a gradient. It's like light,
Oh,
uh,
right.
like
So it's
photonic.
and then conduction is a mixture of. So it has convolute and it just
No,
has
it's
convolute.
a convolute. Convolute is a mixture of both vortex and gradient.
Oh, I get you. So is there anyone with all four?
Energy, the pure energy has
Oh,
all.
right.
The pure energy has all the four.
Oh, that's
So
cool.
yeah, pure energy. Yeah.
That's
So
a
pure
great
energy
idea.
was a pure
Yeah.
entropy.
Yeah.
Entropy versus energy. That's finally the whole deal.
Oh, Jesus, sure, you got a great idea there. You should be
Yeah.
writing. You should
Yeah.
be
I want
writing
to.
that down in some papers.
Yeah. I want to do.
Well, I suppose you are, but it's so high level, like the maths and
Yeah.
all that. It's very difficult.
Alexi said that I can send papers, so hopefully, because it takes a long time. Like the last time, the theoretical it took 6 months for me to write, because all the literature, all the other things. But instead, I want to publish like small results. Without
Yeah.
too much, have to do too much literature survey, or you know. So I just want to theoretical results, so to say, small theoretical results paper, type of thing I want to give it, without having to go through all the literature survey, all these things. Just what my thoughts are, and I will just
Yeah.
reference my own papers and then say this is a result, and eventually we will be writing full paper on that. So it is
Mm,
not a full paper by itself. It's just that's a results paper, theoretical results paper. So like that, so it
yeah.
won't take that much time. Otherwise, even though I'm telling you this, when I start writing into paper, it takes many months with editing and everything.
Yeah.
So
Well, it'd be great. I love to read it. I'll give you a
yeah, so
hand.
I want to produce small things like that, and then you have something also to refer to that to make your research about the 600 cell, 48 cell, 24 cell, and then
Yeah, yeah.
showing how
That would be great.
superluminescent can occur.
We could have
Yeah,
some sort of a gravity thing with the 600 cell,
yeah, gravity. Yeah,
Yeah, this is very
You want
much
to
that.
prove,
It's focused, and then there's all these other little focused points around it. Yeah, that's pretty
yeah,
cool. I mean, of course, not to mention the well, there was another issue there. Well, one thing I was going to say is that your convolute. It kind of reminds me of like a raising and lowering operator or something. It's like it seems like something that's sort of just put in mathematically to do a job, but same. It's probably physical as well. And is it like a field or something?
oh yeah,
But I
yeah,
mean,
you can
it's a
do both.
mathematical thing, so
So
you can manipulate it in mathematical ways, which is very handy.
mathematical on one side, and also you can do a physical on the other side, like geometry and things like that, both. So you can look at the mathematics and then look at the physics the other side and see whether they, correlate or they correspond with each other. You can look at that.
Yeah, that's important.
So you
And then it
two
also
different
reminds me of
perspective.
remember we were talking about the different what are they called? The Boolean logics, zero,
Yeah,
zero, 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 one is one. Could that come into it? I know
yeah.
you
I want to
worked
show
out
that. I
before
want to
that.
show again what I did. Can you let me in?
Oh yeah, hang on a sec. I have to get out of full screen. Exit this. Yep, there you go.
Okay. So here, you see that. Oh, I will go there. I think you can see, but let me see. You can see this now, right?
Yes.
Oops, sorry. Trying to increase. Okay. So the information I call template processing, and I will come to that later. It's an IT thing. Even you can use for because a lot of text and things like that. You can process it much easier, and I have done this. But the 4-vector QN, I call, like Christian was saying, finally, also very similar. It's a quantum n bit, which means that um, it's a four vector thing. Okay,
Yeah.
so yeah, I should remember what I meant quaternion bit. So let me
Oh,
write.
yes, yes.
So it
Okay.
comes with your idea of quaternion bit type of thing.
Right. So you have an on and off. It's a bit like the left and the right spinner thing.
Yeah, yeah. Maybe may have chirality, let's say.
Okay. So what's
Chiral,
going
let
on with
me,
the rest of it?
yeah,
They're tensor products, is it, or something? Each
yeah,
product is a tensor.
yeah. It's a tensor. So I convert, see, this is a tensor thing, right?
Yes.
The time is a tensor. So then it's a 4-vector because it's a tensor. It's a 4-vector. You asked
Yeah.
that question. That's an excellent question. Yeah. If it's just
Yeah.
elements, scalar, then it cannot be considered a 4-vector. But this is a tensor, means a general thing. It can be a scalar if it is 0 tensor, uh, 0th order tensor. If it's a
Rank.
first order tensor, it's like a vector, things like that. So it's more general, the time
Yeah.
vector. And then you can no,
Wait
the
a second.
good
Is
thing
that a
is that
second? Sorry, remind me. Is that a second order tensor, or is that still a half
this can
tensor?
be any order, but it will be maybe up to 4th order, because time
Yeah.
can be in 4th order, right? The 4th level.
Okay. Yeah.
Because the space is, you can say, if you combine all the space together to R, like R vector, I'm showing here somewhere, and if it's like R vector, somewhere, if it's an R vector type thing, where is that? Oh yeah, so R vector, right? The R vector is X, Y, Z together. This R vector is equivalent to, it's just to show equivalence, equivalent to
Yeah.
R tensor, R.
Okay.
I had to put that, the tensor thing on top, like tensor R, which is actually a 3rd order. So it will be a 3rd order,
Rank 3.
3rd order tensor space, right? 3rd order tensor, space tensor R. So 3rd order. So now the time, when you go to the time, it's the 4th order, right? time, when you go to the time, oh, somewhere, I think I have to go down here. Yeah, when you go into the time, it will be typically a fourth order. So time, the fourth order tensor. So with having with fourth order time tensor. So this is like a fourth order time tensor, and then you do this operation like a absolute and what you call normalized absolute things. Uh,
Right.
when you use these things that you are normalizing scalar product, that becomes one.
Is that the
Okay,
magnitude?
but
When you talk about
yeah,
the magnitude or something.
magnitudes. Yeah, so you are actually unitarizing it. So this is a
Oh, I see.
unitarizing.
Yeah.
You are done unitarizing
Oh,
uh, absolute uh, normalization, unitarizing normalized
well, hang on a sec.
something.
When we talk about the magnitude, is that like the square root of the square or something? Is that it?
Uh,
Oh no, it's to do with the vectors and all. Yeah, it's complicated.
yeah, it's a vector. Yeah, you have to normalize it to the. Yeah, you have to
Okay.
do some operation. I will come to that later, but say any matrix, you have to you divide by the determinant, things like that. So determinants, you divide by
Oh
the
yeah.
determinant.
Well, that's
Deter
right. If you want to divide one matrix by the other, you have to get the determinant and then multiply.
determinant, and you divide by that, and then you can normalize it with that process. It's
Uh,
very similar to what you are, what we do with the square root things. You take the square
yeah.
root, the Euclidean thing, you divide by the square root. It's done in quantum physics also. You divide by the square root of the things, and then you can normalize it. Then you can make into digitize 1 0 type thing. So that's what I'm showing here. You can do 0. What I'm saying for is that normally we use only binary, right? Or bit, binary bit, where you have 0 and 1. But what happens if, like in quantum qubit, you have both 0 and 1 together, right? But you can also have neither 0 or 1. So you have the you can have both 0 and 1, and then not 0 and 1. It's like a gate, NAND gate, node gate type of thing. So not equal to 1 doesn't mean it's 0 automatically, right?
Right.
Not equal to 0 doesn't mean it's 1, somewhere in between. Okay,
Yeah.
it's neither 0 or 1, or both 0 and 1 type of thing. So you need
Yeah.
the four things to explain all the things. That's why I call quaternion bit or q twin bit, you can call it.
Ah, that's pretty cool.
Yeah, and then
Didn't
you
realize
have,
that.
yeah, so this is like a circuit,
Yeah.
a circuit, and you have switches. So it's like a switching circuit, and that produces the quantum, the local quantum and the global quantum. So QL is the local quantum, and the QG is the quantum log. So like I said, the timeline and the world line. So so it can interact. It can form like, it can super what you call like entanglement or superposition type thing. So locally, at our like a center of the earth, for example, it can form the QL. At some astronomy, light years away, it can have QG, like a pulsar or something, but they
Mhm.
can interact together, right? They can interact together, and they're showing the charge couple type of thing, interaction. Again, so light years away, they can have quantum entanglement, of the light.
Uh,
And they are shown that Chinese people are shown some quantum entanglement uh, a few meters away or something in space, right? Like
yeah,
like a
that's true.
kilometer away or something. I don't know.
Yeah.
But they are shown that photons can quantum entangle. So this one automatically, this is abstract version of that. It's all from the mathematics. I'm showing that this is possible. Now, For the physics, we know that some of it is proved, not all of it is proved. Now, I use very similar to your technique of using the curl bracket like this. It's much easier. And then, the square bracket, which means the same thing, it means equivalent. But now I can express it, in one
Yeah, but
line.
if you're, are you doing like a matrix multiplication on top? So you get 0, and then you get,
Yeah. So when you,
yeah,
yeah.
you get
So
0
when you do this one,
0 and not 1. 0 and not 1.
yeah.
So
Yeah. When you actually evaluate, like the value will be 0 times, what do you call it? 0 times off, on,
yeah,
sorry,
yeah,
plus 1 times off, right?
which is 0, is it?
When you multiply 1 times off, because when you multiply this one, then multiply these, right?
Yeah.
So that becomes, when you add them, that becomes equal to QL, right?
Yeah, but what is that? Is 0 times on nothing, or is it on?
So in this case, yeah, what I'm saying is that's why I use this one. You can permutate the 0. This can be 1, this can be 0. You can permutate the matrix. But in this case, the QL, in this particular instance, the QL just becomes off, right? Because 0 times on is 0, theoretically.
Oh yeah, of course it becomes off. Yeah, I get
Yeah.
it. Yeah, sorry, I was thinking about that completely.
Yeah, but I can change this. Suppose this is 1, then the QL becomes on, right? So you have permutation of this one. You have to permutate on that. Okay.
Yeah.
This is a specific value. Or permutatively, I'll say, or permutatively. That's why I show the other one. Permutatively, QL also can be QL can be or can be off or on. The same way, right? The same way,
Yeah.
QG also can be
not on or.
Yeah, it can be on, off, or can be on or off.
Well, yeah. But wait a second. But what are you're multiplying it by? Not 1 or not half.
Yeah.
Not
So
0.
let me find out that I can evaluate that. So QG, let's say, in this case, QG equal to not 1 times on, right? Yeah, that's a good point. So I have to evaluate like that.
No, not on.
Yeah, not on. Exactly, not on. That's an interesting thing because, oops, move this.
That's not on. And then not off.
Yeah, that can happen, right? I mean,
yeah,
there are states like that. We should describe.
You could get not on, not off.
Not off.
Okay, and so then your vector that you come out with then is, is off and not on.
Oh yeah. So
QG
I know that it won't be that simple.
No, I'm just trying to follow the logic.
Yeah, exactly.
Possible.
So what is this one, right? What is this one? So not on. So this is not 0, right? So you have not 1 times on is not 0. Okay. So I can say that is not 0.
Yeah.
Right? It's the same as not 0.
It could be 0.
It could be 0.
Okay. The other one is definitely not 0.
So I'll put here
more likely to be not off.
0 or 1. No, 0. So in between.
So it's more likely to be not off than not on, is it?
Yeah, because it's not 0. So it is between on and off. It means,
yeah, because it could still be partially on and fully off.
It means it is fluctuating.
But if it's yeah, what does on off mean? Like, don't answer that yet. But like, let's say on meant if it's partially on and definitely off, then is it still partially on, or is it now?
Yeah, that's
off?
a condition of fluctuating thing. That's a condition of fluctuating thing. Fluctuating.
Okay.
At some point it will seem like off. At some point it seems like on. That's exactly. So it can describe the fluctuating aspect.
Oh, okay, interesting. So is that totally chaotic? It'd be fluctuating in a cycle, is it? Some sort of cycle? Okay. Which would be a combination of permutation. It could be in any order.
Like our PDP.
All orders at the same time.
Yeah, PDP circuit.
Oh, yeah.
Like
PDP. If it fluctuates on and off in all orders at the same time, then that might create a new order, would it?
Yeah. So it can can be
like linear,
it can produce a transition.
What do they call it? The linear combination of all those fluctuations would be a fluctuation, like a Fourier.
Yes.
Fourier,
yeah. So you have complex thing. Yeah.
Cool.
So it can describe the complex things that's going on. You know that I'm trying to say. This very simple. This is very simple, but it can explain highly complex things that's going on because you can.
That's
logically you can have many states.
Yeah. Have you done out the the matrix? I suppose it would be handy to do them out in like table format maybe, and then sum them at the end.
Yeah, I have to. You are good in that, but I will try to do that. Maybe you can look at it and you can probably add more things to it because you have done quite a lot of these things.
True. Well, what I can do is look back on this video because I like these little puzzles.
Oh yeah.
I could try and figure this out as
now it's recorded
as well as yourself. I don't want to.
Yeah. I will also do, but you can also do your analysis because you have done quite a lot of this, and because you are now recorded, right? Recorded video, you can look at it, and and then
which
you can.
Recording? This one.
Yeah, you have a recording, right? You have available now. Available.
Yeah. How it works is just because we're just live streaming to YouTube.
Yeah.
So people now if someone were to click on this for some reason, they're watching us now as we're talking.
Yeah.
Yeah.
Or
and then,
fluctuating.
But then the recording will be left up for forever long.
Okay. What is the how do you access the recording? Is it your thing? Is it your title?
Well, yeah, you could type that into the search engine, but
I should be able to get that.
Yeah. But better, you can do that.
Yeah, last time, yeah.
Because I'm not as I've searched.
Yeah, last time I
searched the title of my last presentation, and our video popped up at the top of the search results. So that's pretty good. But as for you can also just go to the TechNet Earth Global channel and go to live streams, I think, or just live, and just click that, and all the live videos are there. That's another way to find them.
Oh yeah.
Probably the easier way.
Oh yeah. That should be under TechNet.
It's hard to remember the titles.
Can we get this live stream also with the TechNet thing when you put in the TechNet? That's the live stream comes up.
Yeah, you just go to TechNet Earth Global, the YouTube channel, and you go, you open that, go to the channel, and then you'll see videos. Don't click videos. Go to the next one. I think it says live. Click live, and you'll be able to watch this live stream as we're live streaming it.
So let me try to access that right now.
Yeah.
TechNet global. Let me see.
You get some sort of feedback loop. That's okay.
TechNet global Symposia, right? Or
I think it's TEK_Earth. Well, I think you can just write TechNet Earth Global. I think it'll come up when you write TechNet Earth Global. You don't need an underscore. I'm going to be back in 1 second, okay?
And then you go to videos.
You go to what?
Okay. But it shows the other one, how you get a live stream. Oops.
Is it show? Hang on.
Oh, I see your thing now. I see your imputation Earth precursors. I see your Earth precursors. I don't see your first this thing. That's the metric universe. What you have put the metric universe. I'll show you. I can share that.
Well, this
I'll show you what I'm seeing. Yeah, it's interesting.
This is like Inception, you know. You're sharing the live stream as we're live streaming it.
Oh yeah.
Can you do that? Don't do that.
So anyway, I'll finish. So now I'm just summarizing this.
Neither what?
Yeah, I'm just summarizing this. So what I can see with this matrix, very simple matrix, right? You can actually figure out the QL and QG can be on or off or fluctuating cycling. So which means that up in the pulsar, it could be any of them, any of the states. And in the center of the Earth, for example, it could be any of the states. But they can quantum entangle the fluctuating thing, and they can produce highly complex things. That's what I'm saying.
Oh, interesting. That reminds me of
very
something
simple.
I did. One of the first papers I wrote.
Yeah.
That has
very simple algorithm.
Quantum entanglement that links momentum with energy or something. I can't remember what it is. And the two things get switched over. So have a look at that and see if there's any way that could be connected.
You can program it. You can code it easy because this algorithm should be able to program a code and simulate this one, and it can show the whole thing. If you can do that, we can actually publish paper. We maybe are onto something big, granulification. You know.
I think that's very good, though. I like it, but
very simple.
Yeah, it's nice.
I like simple things, you know.
I'm just wondering though, the final step is the bit I'm not entirely grasping.
No, this is just the mathematics, right? You interpret in terms of physics like this.
So let's say the one at the center of the Earth, is off.
QL.
All right, the QL is off, right? So it's a definite thing. The QG that's in the quasar is a fluctuating thing. So
I mean, I can change this matrix, right? I can change the matrix. Where I put 1, 0, I can put 1, and that changes QL, the value of QL.
Oh yeah, I know that. But let's say there's these. So what is the form of the matrix when they are what's the word, entangled, and then they're
entangled? So it means that they have to be in the same state, right?
Sorry, what is the form of the matrix? I was asking.
It will be more like it's more like both of them are fluctuating in some ways, and they find, you know, in general both of them are fluctuating, but at some point in time they have the same state, quantum state. The psi value, the wave function, will be the same, right? It has to be the same or something. The quantum entangle, right? There's a condition for quantum entanglement.
Oh, okay. That makes sense.
It has to be either up or down. Both of them have to be both up or down, or something like that. So they can quantum entangle, something like that. The same state. So the fluctuating means they're going up and down. They're going up and down like that, right? But at some point, in time. This one is up, the QL, the QG also up, so they can quantum entangle.
Oh, cool. Well, I'm really looking forward to reading this paper. This is fun.
Yeah.
I like it.
I think it's a very simple way of explaining all these things, I think.
So when did you come up with this? Oh, you came up with this a couple of months back.
No, this one is very recent. I mean, after we talked last time, like in the last 2 weeks, the last 2 weeks time. Yeah.
Wow, great. And what about the other thing you were telling me about, all the conduction and the heat and radiation with the...
Like a few days ago.
Really?
Within the last week. The last week. This is the last week. So
great, man. I really like it.
That's why I haven't written about it yet.
Yeah, it's very nice. I can follow what you're saying, and it's very pure and logical. So I think that's a goer. Because it needs to be.
Thank you. Yeah.
Nice.
So let me show the site where I'm seeing this now. So I want to share that screen. Let's see.
Rajan, oh yeah, I have to go down to the thing.
Yeah, it's almost time. We are. This is the last one. I just want to see.
Yeah, I'm just going to be back I'll just be back.
Yeah. Can you? We can. Are you able to? Yeah, this is the one you see. You see that? You see here the metric universe, the imputation, your thing.
Yeah, but can you go to the channel?
2 days. Yeah, it's just TechNet Earth Global. That's what I put in.
But that's you're on. Oh, great. You're on YouTube though. You need to be on. You're on Yahoo. You need to go to YouTube. Yeah. So
yeah, but I say video. Oh, yeah. I get TechNet Earth Global video. It shows up.
That's crazy. The video that we are currently live streaming is there.
This one. This one, right?
I can't see your cursor, but yeah.
Oh, let me go there. I have to be on that screen to show.
What's going to happen if we click on that, though? We'll be seeing ourselves or something. Do you want it?
Yeah.
Click on it. Does it let you do that? Will that not crash the universe?
Yeah, let me go. I'm showing.
I see the mouse.
What I'm showing, can you see?
No, I can't see anything. I don't think. Yeah. I don't think they let you do that.
This is the first one.
Yeah. Are you playing it? Oh, I see it now. I see some.
I'm playing now.
Yeah. This is exciting. What are we going to see?
Oh, you see that?
Yeah. Well, I can't see it yet. I can see this. I can see the thing. I can see the thumbnail.
On.
EDEF. Looks pretty sick. See some.
I'm playing now.
Yeah, it's playing now. This is exciting. What are we gonna see?
Oh, you see that?
Yeah, well, I can't see it yet. I can see this. I can see the thing. That's pretty funny. I'm responding to you from previously in the video. I can see the thumb. Oh, nice. Pretty sick.
Yeah, your first.
See some.
First one. I cannot see.
Oh, we need to go deeper. We need to go.
This one.
You need to go deeper, man. To get at least to the third, fourth level of this. Then we could have conversations with ourselves from previously.
I see.
Doesn't let you go that deep.
Oh yeah.
That was funny because you went. Do you see this? And I was like, no, I don't see anything yet. And then when you click play in the recording, you asked it again. Do you see this? And I respond. I thought you were just repeating yourself. So I answered a different way. That's
Oh
pretty
yeah,
funny.
it's a real time. Is true.
Yeah, that's pretty great. Actually, that reminds me of a movie I've seen called Beyond the Infinite 2 Minutes. Search that one up. It's a Japanese movie. What are you trying to search up there, Rajan? Just today's.
Oh, I'm trying to see our this thing. Does it show up?
What are you looking for? Oh, you just click on YouTube, like any link that says go to the YouTube page, or well, it's up to you. Yeah, you can even click on the bottom of the link. Where you see where it says imputation of missing data in STS reveals the. You see 14 days ago, and then yes, there. Click on that link. All right, and then we'll actually go over to the other link here beside it. This one, or any of those. We'll just get to the website. Yeah, try that one. Click any of them. Any link. Yeah. It's probably a bit slow, is it?
That's the imputation, I think. This is the.
Yeah. As long as you can click a link that leads to YouTube, that's what we want to do. Because then we want to click the link. Well, we either have to type it into the search engine there, or the search field, I mean, sorry, or click on the channel name.
ProtectNet.
Excuse me.
ProtectNet Global. YouTube, right?
Well, that's funny. I thought I was trying to understand what you were saying there for the last 2 years, but thankfully you only came up with it on the last 2 weeks. So that's good news.
Oh yeah. This is our earlier one, gauge discontinuity.
I can't see any of that. It won't show me
But
YouTube.
Somehow we can get that. I mean, I know.
Cool. And then you check the live streams, they're all there. I'll send you the link, actually. That would be the easiest way to do it, Rajan, if you can't find it.
Oh, yeah.
That would be a good model for the universe as well, just like an infinite live stream. What do you call that?
Oh, yeah.
Infinite regression.
Live stream catches on itself.
Yeah.
It's like the tail catching the head,
Yeah, exactly. You or me from like 1,000 years in the future talking to yourself in the past or something like that. And all the
you can make a movie out of this.
They kind of already did, like that beyond the infinite 2 minutes. But this is different. So like I'm you from 1,000 years in the past chatting to you or something. And then
there it is. Right now, you see it now?
Because we're talking to each other. Yeah, the quantum fluctuations are all just merging into one universe, which is like this one.
Yeah.
That's pretty cool.
Oh, yeah. So everything is here. Just started, like you said, the search engine.
That makes sense, doesn't it?
And
yeah. There's no such thing as
death. The search engine, put TechNet Global, everything is here, I think.
Oh, all right. You're talking
the first
about
phase
that.
Is the
I thought you were going very deep in the metaphysical thing that, like, if we're talking to each other over like vast distances of time, then there would be no time, essentially.
Oh, yeah.
Like, all time would exist.
So this is our link. Yeah, this is a URL. So let me type in the URL here.
I cannot see what you're looking at anymore. But yeah, that is probably it. So have you just discovered something amazing here, Rajan? I thought you knew about this.
I think we will. I think this equation, what you call the golden equation, type of thing. This may be our simplest equation yet, simplest equation of the whole thing, but in a digital form. You know, it's not analog, but it's a digital form.
Yeah, I can't see
But
what
I
you're
think
looking
you
at.
can program it.
I assume you're talking about the thing that we were just talking about, were you? The
Yeah,
fluctuation thing. Very good. I'm going to be back in a second,
the
Rajan.
fluctuation.
Yeah. Or well, that yeah. I mean, the other thing we could do is, hang on. Well, I'll be back in a second. Yeah.
So let me show you the URL. So now it's quite simple. The URL to get all this stuff. I found the URL. So let me put that URL on this search thing. This is the URL, which gives everything. So I'll put this URL thing, in the next thing, plus URL. So I don't have to list everything. So I say, go to this URL. You see the URL now? Oh, this URL doesn't show up there. Let me see.
All right. I'm back.
Oh,
Yeah,
okay.
I don't think that StreamYard, which is what we stream on, allows you to I don't think it allows you to screen share YouTube, because I couldn't see any of that. But I've seen it all before anyway, because it's our channel. So
I have put it putting in the chat our URL. If you click that
great.
URL,
yeah,
the URL, we don't need so I need only this one from now on. It'll bring everything.
Oh, great! Because you see, I thought you knew about this, but I thought you were just what's the word? I thought you were being creative.
Yeah.
with all of the links. It was like
all the listing.
Hey,
yeah,
that's totally new.
Yeah.
But great. Yeah. Well, no, there's another. Is there another way to do it? You can just go. Look, I'll give you another link. Here's another one. This also gets there. Oh, where have I gone? So many browsers open now and tabs. This one works too, Rajan. I don't know where you. That is our actual.
Oh, that's our.
That is the actual one. 29, 23. I don't know the significance of that number.
So we just put in our group email this one, so people can access this.
Oh, that's a fair point. I've never put it in actually. I just assumed everyone knew.
Yeah. So everybody do this now.
Cool.
So there you don't need the listing. I don't need anymore. So this is in order. Quick. I hope it shows. Doesn't show our
No, it doesn't. You have to click into videos or live to do that. For instance, if I go, I think you can just put /videos at the end of it, or /streams. There's where the live stream is located. Looks like you crashed, Rajan. You've frozen a bit.
Oh, really?
Oh, maybe not. No, you're just really, really still. That's amazing.
Oh, now it's moving. Okay. Yeah, I cannot see the screen when I'm operating. Yeah, that's the problem.
You looked like you weren't moving there for a while.
When I put that URL, yeah, I cannot get the live stream though in that one.
Yeah, check the chat.
Live.
Yes, go to live.
Live.
Yeah.
Oh, live. Go to the live.
Yeah. Great. Yeah. This is it.
Okay. Okay. Oh, so you go to live, you get the live one. Videos, the old one. Okay. So we have to put that in. Put that people say that if you use video, we get all the previous one. If you go click on the live, you get all other things.
See.
Yeah, I think that's...
See, senor, that is correct.
Oh, this one. Oh, these two. Maybe I can put both of them. Let me see.
Sure, why not?
Oh, you have to show. You need the 2%. Okay. So I can put both the URLs, and they say if you old one can get this one, right? The first URL, and the live stream one, all our new ones, the phase 2 ones. So I don't have to put the list.
That is amazing, isn't it? That you set up the phase 2 thing just as we went to the live stream.
Yeah.
That's weird, isn't it?
Yeah, it was like a conjugation of our thoughts, you know. You are in the same level of thought. I mean, it's like it's like a superposition or quantum entanglement of our thought. We are in the same wave function.
But then so does John as well, because John is obviously the deconvolutional matrix that moved off, and then
yeah,
or the other one.
These are things I want to talk with him, but it's okay. I think we can progress further. You know, we know.
Sure. Yeah.
We have the algorithm now. We have the algorithm.
That reminds me,
the binary algorithm.
Well, he's big into the heat and wave thing equation and the problem there.
I think we solved the thing.
Wow, great. Good for you. That's great.
I think this convolute thing, the 4-vector thing, will solve that problem. Also, double slit. If you explain it properly, I think we can explain all these things.
So when you're saying the 2 waves cancel out in a double slit or interference pattern, does that generate heat or no?
No, when it hits an object, if there is a what you put a block. What is it called? You put a
screen.
It's called something in the double slit. You put a screen.
Panel. Screen.
Somewhere in between, you put something that's called. John uses a term called. What is the term?
Oh, obscurant or something.
Is it object that's in the middle, like a nail he puts?
Yeah, that's right.
He called it something. It's called something.
I think it's the flip. Is it the Here's here.
I think I have it somewhere. His thing. I have so many things open.
Yeah, me too.
I like million things, million down the computer like anything.
Is this going? Yeah, is this going back? How many months are that you have these tabs open?
Oh, transfer mask. mask.
Your computer's dying.
Transparent mask or
transparent mask. Yes. Or what?
Yeah, mask. So if you put the mask, then it creates the mask will create the heat. You know, the heat will like conduction. You know, it goes through convolute field will go in, and then the other one deconvolute. It meets the convolute and the deconvolute meet together, and they can create interference pattern or diffraction pattern depending on how they are oriented. Yeah.
Have you figured that out yet, Rajan, or you're just hopeful that this is?
Yeah, I think this is the idea. I think I think with this we can explain the whole thing, but it takes a little more, few more papers. But I think we got an idea. You know, the main concept. This is the main concept.
Yeah. Well, I have another big idea. I have another idea. I don't know. I mean, is it worth sharing now? I mean, were me and you talking about catenary curves or something?
Quaternion.
You know, catenary. It's saying it right. Catenary curve. Like if you were to hold, like if I were to hold this, you see that right chord. See the way that it. Well.
Yeah.
See the way it flops down like that.
Yeah.
It's kind of.
Yeah.
That's not a very good example of a catenary. Oh, here. This. Oh, flip. There's a knot in it. Hang on a sec. I think this is going to be difficult to see. I might have to switch the light on. Flip. Hang on a sec. Should be a slip knot, no? Yeah. This. You see this? It's so hard to figure out which is right and which is left. That's
a chain. Is it like a chain?
Yeah. Yeah. Chain. Exactly. So the middle link at the bottom is being held up by all the links on the other sides, but it's also holding up the links on the other sides. Yeah.
Yes.
So I use it as like a model of time. So the present moment is the link at the bottom. Yeah. The chain is like being pulled up at one end and lowered at the other. So the link, but it's an infinite chain. It doesn't matter. And the link at the bottom just moves along one space. Yeah. So then if we were to track the motion, well, the link moves up or up the other way. And so the new link comes in and that's the new present moment. And then so on and so forth. Sorry. You know, another
so it
link
moves along that. You say it moves along that.
No.
That curve. Along that.
Well, yeah, like maybe I can do it here. So if you imagine what's at the bottom there, and then
yeah.
If I'm moving this, but I'm also moving this way at the same time. Or this way.
It goes up and down.
So like if you imagine the point at the bottom, was, let's say it was touching something like a book. Yeah. And if I were to flip. Sorry, I had a drink. This is really nothing on my mind. Yeah, I had it there a second ago. You raise this one, lower this one. This must be really annoying for anybody watching this. There we go.
You will figure out some simple way.
Yeah, but so anyway, what happens is you move it along and you move it in one direction. And so a different part of the chord is always touching the book as it moves along. Yeah. So then if we were to just take the part that's touching the book and like cut out everything else, because that's the past and the future that doesn't exist, then we just have a straight line so it's like lying the chord flat on the book, because every point is now represented on the book. But this is a four-dimensional line in the sense, but so is this as well, you know. But so the interesting thing about that is that the line that's in the future, so like the infinite future, this side, or this, but this side, let's say, is like this. So it's a 90-degree angle to all the other times. So we could do like a dot product on that, and then you say like A dot product B at the same, at the same instance in the present is 0, I think. But A dot product BT1 is also kind of 0 because they're very similar, close to 0, I guess. That, or I might have written that wrong, but like A dot product, oh, sorry, A being the catenary curve, B being the straight line of all of the points. So A dot product B of T being time in the infinite zone is 1 because in the infinite zone, when in the catenary curve is orthogonal to whatever A is, so therefore that's 1. That's what I meant to say. But A goes to B T in infinity, dot product B T in infinity is also 1. So you can start writing like weird sentences like the future of the present is the maximal distance from the present of the future. Maximum distance, maximum distance being the angle between the two moments.
With similar timeline and world line, I'm talking about, it's more distributed, but you can convert, you can use this idea for, to
it's very
describe the
relativistic.
future.
This is highly relativistic because you're talking about something that's like 90 degrees, so therefore completely at the speed of light. It's totally length contracted with respect to the A moment in space or the B timeline.
You are not saying dot product of the 90 degrees, right? You are saying because the dot product had to be 1.
Yeah, A and B is so A at the
like this.
The very base of the catenary curve touches the book, but that's also a moment in space. So those are parallel. So they become A dot product B would be 0.
The tangent of the curve. Right?
Although actually, sorry, if I got this wrong,
tangent. The tangent plane. The tangent plane. You are talking about tangent plane of the quaternion, right?
Well, yeah, you could look at it that way. Actually, that's interesting. What I was thinking, sorry, I have written here that the dot product, if two things are in alignment, their dot product is 1. Is that what you're saying?
Yes.
Oh, flip. So maybe I mean the other one then, the cross product. That's weird that I got that wrong again. Just goes to show.
Yeah, if it is the same line, dot product will get 1. Yes. If they are 90 degrees, the cross product will give them 1. They are at 90 degrees.
Oh, right. So I must have screwed something up there in terms of my. Yeah, I've got it here. No, I don't. I'm going to have to look at this again a bit more closely because it looks a bit more complicated than I was thinking.
So your A is your tangent plane of the quaternion curve.
Well, yeah. Well, no, actually, isn't the tangent plane the flat one? So that would be B.
B, yeah. A or B, whatever. Yeah. A is your this one. A is your the straight one, right? The straight one, right?
Well, okay. In this, if you want to say the straight one, yeah, that makes more sense. It's better to have A.
And the B is the tangent plane, of the quaternion.
No, hang on a second. But the tangent plane is the straight one, isn't it?
The plane is straight. If it's like this, right? The bottom one, that's a tangent plane. That's a straight one. That's a straight.
Yeah. I agree. Yeah. Okay, that's cool. So the future of the present is the maximum distance from the present of the future. So let's just call it a dot product, but we could call it a cross product. Assuming I've got this right. Yeah. So the dot product, like the cross product, therefore how similar the distance and or energy is, because distance and energy are similar, right? Or it could be even considered the same thing. So how similar the distance under energy is works in the 4th dimension very similar to 1, either no energy. Oh, that may be it. See, all this seems to be backwards in some weird way. 1 is no energy, very different to 0, so lots of energy. very different. So if the angle is very different, it's 0. So that's the dot product. Hang on a sec. No, that's not. It's the cross product. So yeah, but then, well, okay, so that is interesting because if I go on and read here, it says the cross product doesn't work in 4D spatial dimensions. It looks at how different the two energy vectors are from one another. So very different equals 1, very similar equals 0, no energy. There are an infinite number of vectors in the first case, therefore an infinite amount of energy. Infinite amount of energy could explain many things, including Heisenberg's uncertainty principle. That's what I mentioned to Emmanuel the last day. And possibly vacuum catastrophe, I'm not sure. So yeah, so it goes on, and there's more stuff here, but I'm a little bit confused about the dot product cross product thing now. I'll have to yeah, when they're different, it's 0. So
yeah, dot product, if they are different means 90 degrees.
Yeah, and then it's 0.
Yeah, it has to be 90 degrees, then 0. But any
Oh,
other
that's right,
angle,
then.
it's a mixture. Yeah. It's a mixture of.
Yeah. So that's what I've got here. So it's right. The dot product is how similar the energy under distance is. You know, it works in 4 dimensions. Yeah, we know that. So if it's very similar, it's 1. If it's very different, it's 0. And so 1 is no energy because there's no difference. 0 is lots of energy. And the cross product doesn't work because very different is lots of energy. Very similar is no energy. Which there are an infinite number of vectors in the first case, in the very different case, therefore an infinite amount of energy, which just means to say there is an infinite amount of energy in the 4th dimension. Right? But I mean, you can say that about the 3rd dimension as well, I suppose.
Yeah, superluminous means, yeah, superluminous could imply that.
Right. I mean, it could go on. Like, if we could see the Earth from 4th dimension, it would look like the sun, right? Just as looking at a mirror from all directions in space would render it a bright light. Have you heard of that before, yeah? That if you could see a mirror from every angle, it would just look like a bright light. So seeing all events or possible vectors superimposed on one another would not only look bright, it would be a raging fireball of energy, like the sun. Looking at a 3D cross-section of the sun, therefore, would be equivalent to choosing a perspective in the mirror. It would collapse the wave function of possibilities, and the sun would freeze into a solid material 3D object. On this object, it is, from one perspective, entirely possible that there are cars, trees, and people going about their work. In fact, the sun may in fact be the mirror of the Earth, or more correctly, a 4D information storage and projection device of the current Earth. That's what I'm saying. Anyway, so these are just like mad thoughts, but it's kind of fun.
So like very similar to matrix simulation. Matrix, you know, like the whole world is a matrix, you know. Matrix
Yeah.
You know.
Well, I'm kind of thinking, you know, I mean, this is just one way you could go with it, but so I think the core concept from earlier seems pretty sound, but you know, you can go on. Events from the future are streaming onto the Earth from the sun and affecting the present in terms of moods and geomagnetic fields, weather, and earthquakes. Oh, that was another point I had about the because well, the ancient Greeks used to say that the sun was a mirror. That guy Robert Bataille says the sun is a surface that is a crystalline lattice, which is kind of like a mirror. But yeah, because we were talking about the earthquake preparation zones earlier, and that did remind me of it. But oh yeah. So just like the way there's all these cracks forming and resealing and forming again, and then finally there's the big, you know, explosion. I was thinking you could possibly do something with lightning in that regard as well, like almost like an earthquake is a lightning bolt underground. You know, something like that. Like it's like this huge shock, like as it.
Yeah,
as it
that's
sinks.
unified.
That'd be
That's
cool.
why that
Yeah,
unified field, you can probably explain it. Like QL and QG, you know, how they initiate. The QG can initiate QL, and so that's a mechanism, you know, where the astronomy, the astrophysical thing can affect the Earth thing, you know, through magnetism, you know. So it can activate the fault, you know, the magnetic action to produce the fault line, things like that. So it produces.
Sorry. Oh yeah.
Yeah. So it can interact somewhere up in pulsar, something happening. The magnetic thing can affect the Earth's core, and it can start activating it. You know.
Okay. Yeah. I have to think about that.
That
is interesting. I like it. I like the QL QG. It's got a ring to it.
Yeah.
It could be the next, you know, Q factor or like any of these constants, alpha constant.
Yeah.
QL QG. It's good. It's got a ring to it.
Thank you.
Yeah. The whole thing sounds pretty interesting as well, and I think it'd make a nice paper, like, you know, nice logical thing that follows along, and it's pretty
connecting
cool.
things.
Yeah, and the other one is very good as well. So awesome. Okay, Rajan, I think we'll sign off on that.
Thank you.
It's been 4.
Thank you. It's a long distance. Yeah.
Excellent. Okay, and that was really good fun. See you next week. Oh, by the way, on the issue of next week, I have a. I could do another presentation. We'll see.
Yeah.
But
yeah. Go ahead.
If there's nothing going on, I'll do it. Because
I don't think there's anything now. You can go ahead and present.
We could even do like a short one, and then if somebody wanted to do something afterwards, it's no problem. So cool. Okay. See you then.
Sounds good. Great presentation. Thank you.
I'll send you some more info on the presentation later. Not now.
Yeah.
Okay.
Appreciate it. Yeah. Fantastic. Have a good night.
You too.
Yeah. Thank you.